Good morning. Ladies and gentlemen in the back, please move forward. Those in the middle to move forward. Let's fill the seats in the front. Yeah. Please come all the way to the front so that those who come late will fill in from the back and not be disruptive. Thank you. Come all the way to the front. So can I take this one? Good morning once again. It's 9:30 and we are late. So we'll go through the program as quickly as we can so that we can make use of time prudently, yes. My name is Danielle and I'll be your MC for today. We're going to go straight into scientific session 3. For this scientific session, we're going to be chaired by Mr. Kwame Desewu, who is a senior entomologist at Anglo Gold Ashanti Malaria Control Program. Mr. Desewu. To assist Mr. Desewu, we would have Christopher Nilayeteria Mensa of the Parasitology Department here at Noguchi. Thank you, chairpersons. Chairpersons, your audience.
Thank you very much, Daniela, and good morning to everyone. You are welcome to today's session. The session on vector surveillance and monitoring systems. So this is a sequel to the previous session we had yesterday. And this session will also tackle modeling for effective management of vector-borne diseases. So I'll be doing this together with Nilai. Right, so we have a number of presentations lined up. I think from the program we have about 6 presentations. First will be the plenary. So for the plenary, we'll have Dr. Andreas Kudom from the Entomology Department of UCC, who will be presenting on the molecular identification and knockdown resistance mutation of bedbugs involved in the 2019 outbreak in Cape Coast, Ghana, and Munich, Germany. Right, so Dr. Kodom, you have the floor. Thank you.
Thank you, Chair. So, my name is Andreas Kodom from University of Cape Coast. Among the insect vectors We have some that are very dangerous, like mosquitoes. And we have others that are feared. So this morning we are going to look at one of them that is mostly feared, and that is bedbugs. And we will look at the molecular identification and their resistance level. And in 2019, so as we go, we will see why 2019 is so special for the bedbugs. So without much ado, so this is bedbugs, and when they lay eggs, they have the incomplete life cycle. So the egg will hatch into a nymph, and we have about 5 nymphs before they become adult. And they are ectoparasites. And primarily, they will feed on humans, bears, and bats. And they feed on blood. So the male, the female, all feed on blood. All the nymphs feed on blood. So their blood feeding greatly affects the quality of life of its human victims. And this, the major problem is the nuisance. If your bed has been infested with bed bugs before, you will see the great discomfort. Others have even allergic reactions and different skin problems when they are bitten by bed bugs. And the most important impact is the psychological impact of bed bugs. There was this research done by Siedel and Rehat at Germany, and most of them feared bed bugs more than even mosquitoes and other vectors. So this shows how important bed bugs is in terms of vector control. Yes, there are quite a number of pathogens that have been isolated from bed bugs, but some, as at now, they are still not regarded as a vector because they have not seen it in transmitting any pathogen in field settings. So though there are many pathogens isolated, they are still not regarded as a vector of any disease. The bed bugs and humans, we've been having this relationship for a very long, since the beginning. But at some point, around 1950, 1960, when malaria control in other Europe and other countries were at the peak, bed bug appears also to vanish. But recently, they've reappeared, and there are quite a number of outbreaks around the world. The most important species that are associated with humans is the C. letularius and C. hemipterus, the common bed bugs, and the C. hemipterus being the tropical bed bugs. And they have some kind of geographic distribution, where C. letularius is found mostly at the temperate areas, Europe and America. Then we also have the tropical bed bugs distributed in the tropical and subtropical areas in Africa and West and East Asian countries. However, they are now even expanding, each of them is expanding their territories. So we have even letularius now being seen in some African countries, while hemipterus, the tropical one, has been established in some European countries. And if you see this map, so the green is where the common bed bugs are distributed, the temperate areas. Then the red is where the tropical bed bug is also distributed. We have the red and green slash is where mostly they overlap. But when you see the dot, the red dot in the green, that is where now the tropical bedbug is now expanding their territory too. So you could see in a number of European countries, they have been identified over there. Again, if you also come to Africa, you see some green dots also in some countries, showing that the C. letularius, or the common bedbug, is also expanding its territory in where traditionally they were not found. And if you look at the map with the countries, you could see some distribution. So the top there is Sweden. You could see that as at 1994, there wasn't even any outbreak. But 2019, there was a spike. So as Sweden also spiked. Then Australia down there. This shows how serious the resurgence is. And mostly you could see the 2019 over there. Yeah. And this article sample some bed bugs from almost all the Central and Eastern European countries. And as of 2019, they identify that the tropical bed bug have established in some of the countries like Czech Republic, Slovakia, and Switzerland. And that was the first time that they saw the tropical bed bug over there. And this resurgence of bed bugs have been attributed to the increase in international travels, also immigration, the trade in second-hand items, then insecticide resistance, and it's due to poor management, which is increasing this resistance in the bed bugs. And all these problems has come together to affect or increase the resurgence of these bed bugs. And we've talked about Europe, and Ghana was not also different. In 2019, there were quite a number of outbreaks. This news item was talking about St. Peter's SHS, how the management was raising alarm on the infestation of bed bugs. And during 2019, many schools were also closed down, especially high school, because of bed bugs infestation. And even some of the universities, like University of Cape Coast, also had serious outbreak in there. Besides Ghana, there was also outbreak in European countries, and one of them was in Germany, Munich. And this happens in some of their refugees camps. There was a serious outbreak at that time. But to be able to manage this outbreak effectively, you need to know which species is involved. And of course, their insecticide resistant status. But why are we concerned with the species? Because these two species that are overlapping and expanding their territories, though very difficult to distinguish morphologically. However, they also have certain morphological and physiological differences that affect management or control. For example, the tropical bedbug has greater number of tenant hairs on the tibia, and because of this, if you use commercial traps to trap them, it's one of the ways that they use to manage bedbugs, especially in Europe. You trap them, because of those hairs, they are able to escape from the . For example, the work that was done here, which used PCR, but as of 2019, it was still not published. It was on the internet as a thesis. Again, most of the resistance or insecticide tests that was conducted were mainly through commercial formulations. There wasn't much studies using standard like WHO insecticide biopsy or even the technical grade of the then there wasn't any KDR mutation information on the bed bugs in the country. And then also they didn't know the KDR mutation at that time. So this gave us some research. And traveling and also found himself there and even responsible for Cape Coast and Munich to answer this question. So in Cape Coast, bed bugs was collected around about 18 communities, as well as educational institutions like the high schools and the two tertiary institutions, the Cape Coast Technical University and University of Cape Coast. Again, in Munich, bed bugs was also sampled from refugee shelters, and they were all taken to the lab. So in those places, whether households, dormitories, or hostels, the items that were infested, we brush off the bed bugs, including crevices and any other potential places with brush into a plastic container. And these insects that were taken to the lab was used for the WHO susceptibility test and also the KDR and species identification screening. So 40 samples was used in, for the identification, because the areas, the households that were collected, we would group them into 7. Then in each of the 7 places, 5 bed bags were taken. Then in Munich, 5 bed bag was also taken, making it 40. And these were, PCR was done, followed by sequencing. For the species ID, we use the PCR using the cytochrome oxidase subunit 1. Then we also look at the voltage gate channel gene for screening the KDR. So with the KDR, where we sequence, we're looking for these putative KDR mutations. For the lentivirus, we have about 3 in that gene that we see. And for C. hemipterus, there are about 9 mutations that have also been identified in the gene that we sequence. For the susceptibility test, we used about 5 insecticides. DDT 4%, permethrin, the diagnostic concentration was 0.75. The permethrin, the diagnostic concentration was 0.05. Then bendiocap 0.1. But after initial exposure, we needed to increase the concentration, so we took times 10 of the diagnostic concentration. And the exposure time for DDT, the WHO recommend 5 days exposure. Then for the others, it was not very clear, because for phenyltration, the recommendation was 24 hours. Others, it was bendiocap, it was about 5 hours. And permethrin and the permethrin, there wasn't a clear exposure time. So we used 24 hours for all of them. And this is how the WHO susceptibility kit for the bed bugs look like. It's a glass, and for per insecticide you use about 5 replicates. So you have the treated papers, you fold it, put it in the glass, then one of the glass serves as control. So in each experiment you have 5 replicates and 1 control. So this was the results that were obtained. So for the bed bugs in Cape Coast, we found 2 subspecies. One that was almost consistent with those sequences in the gene bank, but we have others that were standing alone. Then but all of them were C. hemipterus, which is consistent with the morphological works that has already been done in the country. So we did not find any C. leptularius. And for Munich, it was also mainly C. leptularius, which is also consistent with what they have found in other cities in the country. For the resistance, you could see that the diagnostic concentration was not really doing anything. For permethrin, after 24 days, there was none dying. But even with 10 times the concentration, this is what we were getting. Most of them below 20. And this shows how the level of resistance that they have for almost, so here we have about 4 classes of insecticide: organochlorine, represented by DDT, pyrethroids, represented by permethrin and detamethrin, bendiocap, under carbamate, and phenyltration under organophosphate. It's only DDT that was closer to 40. And this is also shows the reason why most of the control efforts were not working during that time. Then for the KDR, for C. hemipterus, we found two KDR, the super KDR and the 1014F. And this explains the high resistance of the pyrethroids. But you could see the difference between the pyrethroids and the DDT. So this also explains with the super KDR, they don't have much effect, or they don't confer much resistance to DDT. So it was only the 1014 which was having effect, but for the pyrethroid, it was both the 1014 and the super KDR. So you can understand the high resistance again. But yes, sir, though we only did the KDR, but looking at the resistance to phenyltranil and carbamate, we could say that it's not only KDR resistance that is there. There are other resistance mechanism which is working, and there is a need for further studies to look at what are the other mechanisms. Yeah. So in summary for that, the bed bugs involved in the 2019 outbreak in Cape Coast were mainly C. hemipterus, but in two subpopulations. But all of them were resistant, and all of them carry the KDR, the two KDR mutations. And they were super resistant to pyrethroids, DDT, organophosphate, and the carbamate. Also in Munich, Germany, it was mainly C. leftilarius, also having the L925I KDR mutation. But in the study that was also done during the same time in Berlin, they had additional the 418 mutation. So for Munich, it was only one that was found. And this brings us to the question, so how do we control these insecticide-resistant bed bugs? Because it is a problem that almost all the insecticides in the market was not working. And sometimes those that come and work, they don't even want to tell you what insecticides they were using. And most of them, it was not insecticide recommended for public health. So there is a problem that we need to look at how, and there are other methods that, like the use of hot water, and you can't use it during an outbreak. So for the outbreak, we will still need insecticide. So at that time, the new insecticide that was in the market was the Flodora and Sumishield. So, but these were mostly for the malaria, IRS for malaria. So the question was, what would be the impact of this new insecticide on this multi-resistant bed bugs? And can we have a situation where the IRS could control both the malaria mosquitoes and the bed bugs? So that would be perfect. So we also try to answer this question. And here it was in collaboration with Agama. So we send the board or the wood for them to spray with, these were the new insecticide at that time, Flodora Fusion and the Sumishield. Then there was this insecticide, Hercules, which was also on the market, and people were using it for bed bug control. So we had 3. And these wood were treated with the concentration that we use for IRS. Then we double the concentration also, so we have 2 concentration. Then we conducted cone biopsy with the 3 insecticide. So it was done according to the WHO recommendation, 3 minutes exposure, and in each cone, there were 5 bed bags. We use adult bed bags in, and the control was without insecticide. And again, to answer the IRS question, Agama also was making IRS in one of the secondary schools in Cape Coast. So after they sprayed, we also did a cone biopsy on the wall. And also still 5 cones were attached to the wall. And when they sprayed, a week after, we conducted the bioassay. Then we repeated the 3rd week. But for the spraying, they only used Flodora Fusion for that IRS. So this was the results. So this is the concentration recommended for the IRS. But here, both insecticides were only giving about 40, 50 mortality. Only the double concentration gave a significant mortality, but yet still they did not pass the mark. And you could see the Hercules almost doing nothing. Then on the wall, after the IRS, so in the 2nd week, we were getting almost 90% mortality. But the 3rd week, you could see it was declining. Yeah, so in summary, the double concentration appeared to be very good. It was working, and the IRS with the Flodora Fusion also caused a significant mortality. We did in the 2nd week, but the 2nd week was almost 90. So it means the time they did in the 1st week is either it was higher or almost the same the same mortality. So that was very good, but it started declining from the 3rd week. So you still need field assessment to determine the efficacy of this new insecticide. I think there's even more or additional new insecticide with different target sites. And if we'll be able to look at its impact on these resistant bed bugs, it will help in managing them. And again, integrated pest management strategy is needed to combat this resistant vector. So what is the public health implication in all this? So looking at the level of resistance means there will be operation failure. And when you spray and it's not working, people will continue to use more insecticide and even higher, which could affect human health. There was an instance during, I think, 2020 where, due to bedbug control, someone died. Yeah, he used overdose insecticide. Yeah. And this paper also even summarized some of the impacts. And what did he do? So here, they also look at the impact of long-lasting insecticide on contribution of resistance in bed bugs. And they found out that, yes, when they expose susceptible bed bugs to the long-lasting insecticide, it was giving varied mortality, and which could help select the resistant ones. And again, due to the resistance in bedbug, people were not accepting the use of the bed net because they were still having some bites that they don't know whether it's mosquitoes or so. Because of that, they were even refusing to use the net, and there are quite a number of papers on that. So with this was what we were thinking about. Looking at the concentration of the IRS, where there was also given varied mortality, could it also select or cause resistance in bedbugs? And if there are also resistant ones, could resistance also affect the acceptance of IRS if it has to be scaled up? This is the last slide for as we take home. Still some questions to ponder on. Now we have a lot of insect pests and vectors in our household, and we control them differently. Their susceptibility to insecticide also differ. Can we look at how pest or vector control affect these insect pests? You are trying to control, say, cockroaches. What will be its impact on houseflies or others? And can we look at integrated multiple pest or vector management? This could also help reduce the resistance, the potential resistance that we might cause. This work was done by University of Cape Coast in collaboration with Agama, and my chair was part of it. Then we also have collaboration with the Division of Infectious Disease at Ludwig-Maximilian University in Germany. And we thank all of them, and we thank you too.
Right, so thank you very much, Dr. Kudon, for the insightful presentation. I mean, from the presentation, we can see that, I mean, it's very obvious bed bugs infestation is a problem in the country. And I believe it has to be guided by some entomological data if we want to be able to effectively control the bed bugs. So at this juncture, maybe I'll ask, about three questions for now.
Thank you very much, Dr. Kolom, for all right. Thank you so much for the presentation. I need first a clarification, and then the second one is a question. You know that generally with IVM, integrated vector management, when you are doing any control, you want to see that chemical control is the last thing, okay? And so with your screening that you did with the 4 classes of insecticides, I realized that you didn't do anything like PBO, because we have a lot of studies that show that adjuvants, when added to most of these insecticides, it actually enhances it. And so once you were doing something that was a gray area, I was expecting that probably you would want to do that, since all the 4 classes of insecticides were not working. Because if this is not working, then what next? Are we still going out to look for another new insecticide? And you know, most of these insecticides, pyrethroids are always preferred over the others because of other health issues. And so I think the other one, you said you increased the dosage, and it was somehow okay, but it didn't really hit the mark. Yeah, so when you are looking at that, did you consider non-target? And then the harmful effects if, as humans, we'll be inhaling this. So if it is not working, we will not really want to look at increasing the insecticide in there, and then people will now suffer the consequences. So I want to take an example. I was part of New Orleans, their vector control, for a long time. And I know with their cycle, what they do is that there are instances where in a whole year, they don't really apply insecticides. And then nature has its own way of controlling some of these things. In as much as you want to do rotations, but sometimes you want to leave the place fairly fallow. And you know that when it comes to bed bugs, studies have also proven that when you use this leather-coated, Macintosh, you know, in the secondary schools, they cover these things, and it helps. Sanitation is also part, because all these are part of our IVM. So do we want to really look at always insecticides or other ways in which we can really improve it, so that we don't really do a work like this and then bring out suggestions of further studies, but how do we solve the problem? I don't know whether you got me right.
Thank you, Dorcas. Yeah. So the first one is PBO. Sorry, the data is not here. Yeah, we did both permethrin and deltamethrin with PBO, and they were not higher than the times 10. So they were almost, there was a increase in mortality, but not very significant. Then the second question, this was not an intervention. This was an investigation to see why the control was failing. So the double concentration was just to look at if you increase what happens. Because we also have to know that the concentration in the insect vectors differ. So even if you realize the WHO susceptibility test for Aedes, the diagnostic concentration is lower than Anopheles. So, and as we were doing, we didn't know the standard for bed bugs. So we were just using the concentration for mosquitoes. So the idea, if you double it, what happens? So this was not an intervention, just for investigation. And again, there are other control, but we were looking at outbreaks. You know, in most cases, outbreaks, you need the insecticide to, but before that, then if we have others to help so that even it doesn't get to outbreak. So yes, you are right. We need to also look at different non-insecticide methods.
Thank you very much for your presentation. I was just curious. You said that for the organochlorines, you exposed them for 5 days, but for the other insecticides, because there was no clear data, you just did 24 hours. I was wondering why you didn't do the same 5 days for the other insecticides as well. And, well, just the second one also. I didn't see the results for the studies in Munich. What interventions were thrown in, and did they work?
Thank you. So for DDT, normally the exposure time is higher than the rest of them, higher than pyrethroids and the organophosphates. And the exposure time we're giving, for example, phenyltreotide, it was 5 hours. Bendiocap, it was 24 hours. Then in some papers for deltamethrin and permethrin, they were using 3 hours and some 6 hours. So in order to make it uniform, we made it 24 hours. And maybe if we have tried 5 hours, 5 days, Then for Munich, sorry, I did not. We were not able to do the susceptibility test, because we did not get enough bed bars for it. We started collecting in late December 2019, and just January, February, then that COVID came, so we were not able to even enter the shelter again. So we only did the molecular biopsy, not the susceptibility test. Yeah.
All right. Thank you very much, Dr. Kudom. So I have two questions for you. So the first one is about the WHO susceptibility test. And of course, you rightly mentioned that on the blind spot, you had to do that DDs, diagnostic doses for Anopheles gambiae, because clearly they were the DDs for Anopheles gambiae. What stage of the bed bags did you use? Say you mentioned that after sampling, you went on to do WHO test. What stage? Because they are different.
Yeah, adults. We did that.
All of them are adults.
Yes. In fact, we also have names, exposure also for names, and it's almost the same. But what was presented here is mainly adults.
Okay. My next question, it's about the control method. It looks like often than not we talk about chemical control and all, and clearly you stated that we need to find alternatives. We have some entomopathogenic fungus. I don't know if you've heard of it, and it's friendly to mammalian cells, so that means it to be safer for humans. How about exploring that too? Because we have commercial commercial formulations that are effective. How about trying to explore that?
Yeah, thanks. That's a very good question. Yeah, so these are all further studies that we want to carry out. Yeah, so it's in the part of the dreams.
So I think that should be it. Thank you so much, Dr. Kudum.
Okay, so all right, thank you very much, Dr. Kudom. So we move to our next presentation. So that would be Nutifafa Yao Agbeno Efunam, who will be presenting on mosquito track AI sensor, an AI-driven bioacoustic and climate monitoring system tailored for mosquito surveillance and tracking. A round of applause for him, please.
Hello. Okay, good morning, everyone. I hope everyone can hear me very well. Okay. My name is Nutifafa Yawa Agbanafunam. I'm from the Department of Physics, KNEST. Today, I'll be presenting on mosquito track AI sensor, an AI-driven bioacoustic and climate monitoring system tailored for mosquito surveillance. This will be the outline for my presentation today. As we have been hearing throughout this conference, mosquito cause a lot of harm to humans. So a report submitted by WHO in 2004 shows that mosquito-borne diseases cause over 3 billion cases globally. And sadly, this also results in about or more than 600,000 deaths annually. This makes mosquito-borne diseases one of the major public health concerns worldwide. In order to solve this challenge, the approach that is mainly used is surveilling mosquitoes. The traditional method used is by manually trapping mosquitoes and then expert using the morphological features of mosquitoes to identify the species they belong to. And in doing this, this procedure is mostly expensive, labor-intensive, and sometimes also time-consuming. So what can be done to automate this process? Likely, advancement in microcontrollers, artificial intelligence, and machine learning give us an opportunity to use audio to classify mosquito based on their species and also gender as well. This brings me to the aim of this work. So the aim of this work was to design and develop an AI, to design and develop an intelligent mosquito surveillance system that utilizes bioacoustic sensors, climate monitoring sensors such as temperature, humidity, and also GPS modules, combining this with AI to classify mosquitoes. The system is supposed to identify mosquitoes, classify them based on their genus, that is Aedes, Anopheles, Oculus, and then also to tell the sex and then age group of the mosquito. So in order to build this system, we first have to consider the hardware, that is the microcontrollers and sensors, then the firmware that tells the hardware how to communicate with each other. That is the components involved. And then also to develop an interface that will be used to interact with the device, then develop the AI model, and then transmit the data to a database. So in order to develop it, to develop the device, we have the main brain of the device, which is the microcontroller, in our case, an ESP32, and then the sensors that will be used, for example, the temperature and humidity sensor, we use DHT22, and for the microphone, we use IMNP441, and we have some other components like A9G for the GPS, and then a storage as well as an RTC to keep record of the time, and then the power, and then also develop a power system that helps manage the power or the current consumption of all the components. So the design phase involves coming up with a schematic for the device that will be built, and then after that, doing the PCB board. And the PCB board is generally telling the components or controlling the flow of the current to the various components. Then the next stage of the work involved developing the AI model. And in this stage, we have the data collection stage, data cleaning, data exploration. We have the model training, the model evaluation, testing, and then deployment. For this work, we use a deep learning method, and we use the CNN architecture. We converted audio signals into images like spectrogram, like the one shown in the diagram, and we use that, process it with, or use it to train the model that we develop, and later use it for the identification and classification. So moving on to the results, this is a picture of the device that we've developed. We have the control unit, which is the main thing. Then we have the microphone as well as the sensors. That is the DHT22. So some of the features of the device. So the device that we developed has a bioacoustic sensor, which helps to record mosquito sound. We have the temperature sensor, which helps to monitor the temperature. We have the humidity sensor, which helps to track the relative humidity levels. We have the GPS for location tracking. We have storage for storing the data that will be collected by the sensors. We have the interface. In this case, we have two interfaces. We have the physical interface and then the wireless interface. So you can use your phone, connect it wirelessly to the device, and then you have access to the data that is collected by the device, and also to control the device. That is, initiate recording, stop recording, or pause, or do whatever you want to do with the device. We have the recording modes as well. We have three main modes. We have the periodic mode, the continuous mode, as well as the auto start mode. For example, if you put a device somewhere, and let's say you are powering it with solar, and for some reason the battery you are using dies down, and then there is no sun to charge the battery. When the next day comes and then the sun is up and then you are able to charge the battery, the device will come back on, but will it start the recording? That's when the auto start is important. So if you initiate that, then anytime power comes back on, it will start recording. Okay, so we did some lab and field tests as well. So for the lab test, we record mosquito sound. So we put a mosquito. We did this for 1, 2, 3 mosquitoes in a cage at a time. So we place the mosquito in this cage. As we place the mosquito in this cage, we have commercially available microphones that we use, as well as our biosensor to record the sound that the mosquito will make. Then, this is for the lab setting. We have the power bank that powers the device as well. And just to say, the device is designed in such a way that you can use different batteries to power it. For example, if you're on the field, the battery that you might need might be different. So we have a wide range that is from 5 volts to 30 volts. Then for the field deployment too, we went to Ahafo region and then we did some field tests and then data collection as well. So these are some of the field activities we were involved in. So we went to Ahafo region, we placed the trap at different locations and then we record the mosquito sound. As we are doing this we also collect mosquitoes, and then later we performed the manual method that I talked about to do the identification. So in this process, we record the mosquito audio and then later analyze it. And this process also helps us to gather more data for training our machine learning model. So these are some of the results. So we have the data that was collected by the data logger. That is the temperature, humidity, the date, the time, GPS location. And then also the GPS location too comes with a link that you can just put in your browser or click on. Then you have access to the location, or you can view the location in a Google map. Then the temperature and humidity too, when you plot it, you have a graph like this. For the AI model parts, we have, so this is the performance of the model. We have 3 main models that we are working with currently. We have one model that does the genus and gender classification, and that model is at 97%, having 97% accuracy as at now. Then we have the other model that it detects the presence of a mosquito, then also the genus, the gender, and then the sex, the gender, and then the age group. And then that one is at 92%. We have a model that does the binary classification. That is either a mosquito or not mosquito. For the mosquito presence, if you have a particular audio sound, you want to first detect whether it is that particular audio sound have a mosquito sound in it or not. And that is where the mosquito presence comes in. So it's like the first model, you can combine it with the third one, then it becomes a full system like the third one. Yeah. Okay, so for the model output, we have 2 main types. We have the CSV file type that you can just open in any spreadsheet, for example, Excel. Then you can view your data. You can see the probability of the predicted class from the model. And then we have the graphical view. You have the graphical view as well. And then for the graphical view, if you just want a quick overview of the results, then it will give you this. So for example, for this one, it's telling us that it's Anopheles female old. So we have 2 types of, or let me say 2 age group. We have the young and then the old. That is how we train the model. So this one is telling us that. Okay, so almost at the end. So for the current setup that we have, our device records the mosquito sound, that is the wing beat. Then with that sound, you can download it through the interface. When you download it, then you run it through the model on your computer for the analysis, and then you get the classification as well. For our future plans, we plan to put this model on the device itself. So instead of you downloading it and then putting it on the device before getting the data, the device would do all of this for you. Then the result will just be the detection and then the classification results. And some of the benefits of this work is that you have a real-time mosquito surveillance device that you can use anywhere. Then also you can now have a model that will use the climate data that is collected with mosquito activities to do predictions for future work. Then because we are using microcontrollers and low-cost components, you can scale this up so that you can deploy them at different Sentinel sites. Then it also supports outbreak prediction models and then targeted intervention. And it will also help in malaria programs and research. So in summary, we have successfully developed a bioacoustic and climate monitoring device. The device records temperature, humidity, and GPS location, as well as the mosquito wing beat sound. We did some data collection and then used this to train our model. And then the model is able to detect and classify mosquitoes. So about the acknowledgement, I would like to acknowledge our principal investigator, which is Dr. Pedu, my supervisors and other team members, and then also the Director of Public Health, and also our partners, collaborators, and then sponsors. Thank you.
Thank you very much. Thank you very much, Nutifafa. So the floor is open for questions, please.
Okay, Fafa. I want to get this this thing correct. You say we have model 1, model 2, model 3. Like, I don't know the names of your model. And secondly, you say your device. Does that mean your device, it helps in collect? Okay, thank you. Does that mean you use it to collect the mosquitoes, or you collect the mosquitoes and use your device to determine?
Oh,
Yeah.
okay.
And lastly, about you say you can classify the mosquito into like something is young and something like a mosquito is a young mosquito or an old. How do you do that?
Okay.
So
Please, I want to take them one by one, but in case I forget, please just remind me. Okay. Please, just a minute. Please, just give it to her.
I should give it to her.
Yeah. Okay. Please, let me start from the last one, right? You want to know how you detect. So what we do is we record the sound that the mosquitoes make. So in literature, we know that the sound that mosquitoes make are unique when it comes to the genus or the species level. So let's say, for example, we have Aedes. The sound that Aedes mosquito make is different in terms of frequency. And when it comes to Anopheles 2, it's different. When it comes to Culex 2, it's different. And then the male, and then the female as well. Then also the age group as well. So like a younger mosquito, the sound is slightly different. So what our model does is the device records the sound, right? So when you put the device in the trap, as the mosquitoes are entering the trap, they will make a sound as they enter, right? So the device records that sound and then later use that sound to do the classification. So the model classifies that. And our model is a deep learning model that we are building. So we have to give a name to it. So currently we don't have a name for it. But when we are done with it, we have 3 models that we are working with. We may settle on one, or we may do the device to have the different models. So when we do that, then we can give a name to it. Is that all? Or?
Yeah, I think you've the third one that you were answering, you answered like both questions.
So okay. Okay, thank you.
Okay, so thank you for your wonderful presentation. So I would like to ask, how did you have a training data set and a test data set during the modeling?
Yeah, we do. Okay, so for each of the classification that we've done, we have a trained data set and then a test data set. So this is the results from the test data set, not the trained data set. So if you can see, for example, this one, the total number of samples that we use for the test data set is 5,966. We have over 65,000 audios. So this is the one that we place aside for doing the test. So we did training, we did validation, and then test. And for each one, we use different samples so that we can really validate the work that you've done.
Okay, so in terms of the network that you used, you mentioned that
in terms
you
of
used the network, the neural network that you used.
Okay.
You mentioned that you use CNN.
CNN architecture.
So in future, would you like to consider other networks as well, like SVM, ANN? Because in literature, it has been reported to accurately identify them to the species level.
Okay. I'm using audio. If you look at those ones, they use a different technique. And then also, so far for from the reviews that I've done so far for image and then audio, mostly the CNN performs very well.
Okay.
Yes, that's right. But we try with different methods as well. We use MFCCs and then spectrograms and then look at how the results. Yeah.
Please, I have the microphone. Thank you very much. So. I'm very much concerned about the model, the percentage that you shared. You had the binary being 93, and the binary was simply looking at whether it's a mosquito or not. And I'm very worried about the fact that the ones that is looking at the gender and then the genus, yes, is rather higher than the binary, which is just simply whether it's mosquito or not. I thought that one should rather be higher. That's the first thing that you need to start with before you zoom into.
Okay. Yeah. Let me clarify that a bit. So during the presentation, I mentioned the fact that if you have a sound, right, you first have to detect whether the sound is a mosquito sound or not, right? So that is what like the binary does. So detect whether the particular sound you've given to it, whether it's a mosquito sound or not. Then the one that I said that we have 97% accuracy, that one, the sound that we've given to it, so we've developed the model in such a way that the sound that we've already given to, or will give to that model, is already one of the classes. So like whether it is Aedes, Anopheles, or Culex. So they're not like a sound from any other thing which is not part of the class was not given to it. And from literature too, we know that the genus, the sex, and then, the genus, that is Aedes, Anopheles, they have distinct sound. That is how come that one was high. So it's just like looking at mosquito sound and other sounds around.
I get that. What I'm saying is that the first thing that the model should do is to be able to distinguish between mosquitoes and non-mosquitoes. So that should be very, in my view, that should be very high. So there's a percentage of the model picking other insects that are not mosquitoes. It's not, you may not be able to answer that, but that's okay. My second point is the name. You don't have a name for it. Think of Pamca-Ghana for the name. Thank you.
Okay.
Thank you, Natifafa, for the presentation. Yeah, I saw that you were using BG Sentinel.
Yeah,
yeah. And I want to ask, are you also familiar with BG Counter?
Yes.
And does it use the same process?
Okay. No, for the process, no. BG counter, what it does is it counts the mosquitoes. So as the mosquitoes are flying in, they have a sensor in there that uses infrared to count the mosquitoes that are entering. So if like a mosquito crosses that infrared, then it counts it. If it's not a mosquito today, they have a way of identifying whether it's a mosquito or not. So that one gives you only the count. It doesn't tell you the species or any other thing, but it gives you the count, yeah.
All right. This is actually a cheat code, but I have a question. Just by way of clarity, by sound is wing beat.
Yes.
Because you keep saying sound.
Okay, sorry.
It's wing beat.
Wing
Yeah.
beats.
And please define young and old. What do you mean by young and old?
Okay. So mosquitoes that are less than 5 days old, that is what we use in training the model. So we classify those ones as young, and then the ones that are more than 5 days old as old. So we have like 16-day-old mosquito. Like, so when we are recording the mosquito, before we put them in the net, so we have the eggs, right? When they hatch, when from pupa state they move to the larva state, then we put them in the cage. We label the cage, so we know the dates on the cage. We have the dates on the cage. So by the time of recording, we know how old the mosquito is before we perform the recording. Yeah. So we use that to identify how old the mosquito.
All right. Thank you very much, Mr. Papa. A round of applause.
Thank you, Noguchi Fafa. So our next presentation is also in the area of the application of digital technology to enhance vector surveillance. So we are going to have Alice Lechirie, who will be presenting on morphometric analysis of mosquito wings and bodies for species classification using machine learning.
Good morning. So I wouldn't ask if you can hear me. I'd rather ask if you can see me. All right, that's first. So since yesterday, we are from a different field. So it's very strange to us. We saw a lot of different graphs and beautiful names we can use for our children. So I am from the computer science background. I am lecturer Alice Bajere, and today I'm here to present on the morphometric analysis of mosquito wings and bodies for species classification using machine learning. So from yesterday, we know that vector-borne disease is actually a problem to the global, and particularly in sub-Saharan Africa. So when we hear of sub-Saharan Africa, probably we think about the resources and other things. But when it comes to vector-borne diseases, it's actually very sad for sub-Saharan Africa. And we are talking about an annual death of over 700,000 mosquito-borne diseases that are causing globally. And also we can talk about Africa taking a percentage of 94% of this global malaria infections. And in talk of this, we are saying that less than 5% of research actually goes into machine learning classifications using images. So Ghana is not an exception. I have actually been privileged to join some of the entomologists in the lab to do some classifications using the manual way. That is looking through the microscope and actually identifying which is which. And I can best say that it is very stressful, time-consuming, and then I don't know, anytime I get up to stretch, I find the importance of my work. And also we can say that the data limitation is, so we have data limitation in the global world. It means that African-based data sets, when it comes to the images of the mosquitoes, are underrepresented. And therefore, there is a need for advancement in our data sets. And also, we know that Africa as a whole is limited when it comes to advancing technology. So as an entomologist, I know that you think that if you automate this process, it means that my 15 years of classifying mosquitoes or identifying mosquitoes will be taken away. Actually, that is not the case. I think we'll find another job for you. So this is where we come in as computer scientists. So over here, we are saying that we are applying CNN or machine learning-based models or algorithms where we can use to automate these processes, that is identifying and classifying these mosquitoes. And then our research objective for the scope of this study, we are actually classifying or we are identifying two things. One is the wings of the mosquito and another is the body of the mosquito. So you're trying to see that does it differ in any way if the entomologist or if the machine learning model will be able to use the wings only to classify the mosquito or use the body only to classify the mosquitoes, and which one gives us a better accuracy and prediction. So here we have the methodology flow. So we have our data sets, which was actually, so it was a mixture of public data sets and also our locally collected data sets. And for this study, it's only on Aedes mosquitoes, tailored down to the 4 species of the Aedes mosquito. And then you can see our data training flow. We have where we go to the pre-processing stage where we have to clean our data. It's actually called data cleaning, where we have to clean our data. They say that data is oil, so what you feed your machine learning model is what you're going to get. So we make sure that our data is clean as clean as possible, then we can train it with our machine learning models. And when you go to the machine learning models, I think Fafa was asked, so I am using the CNN model for classification, both for the wings and for the body. So let me speak a little bit about that. So we have pre-trained models. It means that other scientists have already trained some models with large data sets, which we can adapt in the field of mosquito classification to do our classification for us. But the challenge is the weight of these models. Sometimes it's quite too large for us to deploy on our mobile platforms or IoT devices. Therefore, there is a need to tailor down the weights of our CNN models. So for the scope of this work, we actually created or trained on a custom CNN model. That means we created our own CNN model, which will be lightweight and can fit in on our mobile devices or IoT devices. And then we have the evaluation metrics, which we use to benchmark this results. So here, I am from the computer science background, so I find this work quite fascinating because we have to go into the field. I don't know why the video is not playing because it's supposed to play. But then let me just explain. So we went to the field, and then that is me over there with I don't know, ladle. It's like I'm drinking something, but then I was only identifying if there are any pupa or larvae in the collection. And then over here, we brought it to the lab, and we're able to. No, the video is inside. It's inside the slide. Yes, yes. Which one is it? This one. Okay, it's actually a video that we went for data collection one time for Anopheles mosquito. And actually I got stuck. They said step where I stepped, and when I stepped there, I got stuck. So that is actually the video. But that day, surprisingly, we had no catch. We didn't get any catch. So moving forward, yes, I think so. So moving forward, this is the data set overview that we use for this analysis or this study. So we have the body only and we have the wings only. And for this study, the bodies and the wings were actually collected or were captured using the microscope and the normal mobile phones for classification. So when it comes to the experimental design, so as said earlier, we have 2 classifications that were done. We have the wings-only classification among the 4 species of the Aedes mosquito, and then we have the body-only as well. So the data split was actually done in 70-15-15%. That is training data set was 70%. We have 15 for validation, and we had 15 for the testing data. And then each model was trained for 25 times. It means the 25 epochs. And we use the cross-entropic loss to calculate for the loss function and the Adam optimizer to actually update the weight after each epoch. And then that is the data flow, or that is the flow of how the data was trained. So we have the data set, we have it going through the pre-processing stage, and then our custom CNN model. Then we have our evaluation metrics. So when it comes to the results, we actually found something interesting. So most work, or from literature, most of the work has actually been done using the body only. But then recent literature is actually finding if we can also use the wings to classify these mosquitoes, and therefore making this work interesting. So when it came to the wings, we got a training accuracy of 98%, 98.3%. And we got a validation. It's like, okay, so when it comes to deep down CNN, so we have the training and the testing. And when you break down the testing, we have the testing and the validation. So all that comes into testing and then training, sorry. And then we have that also benchmarked against the test data sets, which gave us an accuracy of 87.4%. And with the confusion metrics, we are trying to see if our model actually did a good classification. And as we can see, for the wings, it actually did better, but we have some misclassifications over there. And similarly for the body, but we see that the wings actually performed better because the body have an accuracy of 75.4% and a lot of misclassifications when it comes to the confusion metrics. So just comparing the two, we say that the wings performs better when it comes to accuracy, and we are saying that it means that the model, the machine learning model that we have, was able to actually find some distinctive features in the wings as compared to the body. And we are saying some problem could be the background noise or the similar morphology, because we're using the same, like Aedes mosquitoes, but then the species level. And then we have the visualization. So this in machine learning models or machine learning algorithms is actually trying to explain what the machine learning used for the classification. So it's just like giving a doctor the accuracy of 87 and saying this is the drug I have produced and use it to help people. So we try to explain what aspect of the mosquito did the machine learning model look out for before doing the classification. And we can see here that for the wings, it was looking at the wing veins to do the classification. So we have much heat map around the vein units. But something interesting we found out. So we found that when it comes to the body, it is actually the concentration is actually at the legs parts of the mosquito. And I will say that when you are like in research, the more you find your research, or the more you find a solution to your research, the more you're finding problems. So could this be that there is an option for us to consider the legs of the mosquitoes too when it comes to classification? So in my concluding statement, I say that there is a potential for automation of mosquito classification. Like we have the potential to actually automate some of the things that we do manually as entomologists. And also there is a high chance for wing-based models to be used against the bodies as it is being done. And for future work, I mentioned earlier that we have very less data set representation when it comes to the global world. So we, as a team, we are creating our own Ghanaian data sets, which you can see the image over there. So we have it divided into two. We have the early stage and the adults. So for the early stage, we have the pupa and the larvae of the three genus of mosquitoes. That's the Aedes, Culex, and Anopheles. The same thing for the adults, where we have it subdivided into the male and female. So how does this affect, or how is this important to public health? So we are saying that we are creating a fast, accurate tool for species surveillance in Ghana, and also a reduction in dependency on entomologists in the field. Also, we say that this will support early detection and targeted interventions for disease control, as well as this can be adapted on our mobile platforms or IoT devices for public workers. So this is an acknowledgement. Our principal investigator, that's Dr. Bedu, my supervisors, and then we have our partners and sponsors. Thank you.
Right, thank you very much, Alice. So at this stage, we want to invite 3 questions.
All right. right, thank you very much. Great presentation. Just to find out, any particular reason why you chose to use this for the machine learning classification?
No, not very specific. So actually, the data set we found online had the body and the wings. We are now developing our own data sets, which is on way, and we have already over 10,000 images for the body, the early stage, but then we are still to deploy more images when it comes to the wings. So there's no specific reason why we chose only 80s. Yeah.
Thank you so much for the presentation. I wanted to find out, you're not a vector biologist, but how will this machine learning work in identifying different, we have another species complex. Maybe one species, there might be different, can't identify different strains within a species. In a species complex, like another Gambia complex, for instance. And then also, my second question is, talk about the wing veins. You know that the veins of the wing can change with different ecological zones. If you move from the north to the south, the wing veins can change. Please affect the result of your study. And how do you intend to factor it into it? Thank you.
Yes, please. Thank you very much. So I did not get the first question, but the second question, I actually got it. So this is not we doing it manually as mosquitoes move from one stage to the other. This is machine learning models using their algorithms to really identify what are some of the patterns in these wings or in the body of the mosquito to actually do the classification. So when it comes to the machine learning aspect of it, it's like it's limited to the models that we build and how intelligent the machine is to identify this species.
Okay, thank you. So I will just reiterate his question. First question, he was asking, given that Anopheles gambiae is a complex, meaning it has different sibling species in there. He was asking if your model can also help to identify those individual species.
Oh, yes, yes. I am not so much into the biology things, but I think it can. If it's able, just the thing is that it should have some distinctive features that the machine learning can actually use to do the classification, and that it can do it. Yes, please.
Okay, so thanks for the presentation. Thanks for the presentation. I think it's just a suggestion. You asked why the algorithm, particularly for the body identification, was targeting just the limbs. And I think with some little knowledge, I think maybe because the earlier algorithms have been uploaded to identify the mosquito species by their hind limbs. And that comes also in handy when you are doing there's something called DNA barcoding. So in DNA barcoding, they actually use the hind limbs of the mosquitoes to identify whatever species. That's it. So I'm thinking maybe that could answer the reason why I was identifying the hind limbs.
I doubt.
So for your identification, complex, maybe Anopheles gambiae complex, Aedes, more of, if you're talking about the sibling species, it's more of genetic. So I don't know if your system can identify.
Okay, I think it's a wise suggestion, and we are going to look into it. Thank you very much.
So I was going to just also indicate that we've answered it for you. You cannot identify it.
Yes, please. Thank you very much.
Because the machine focuses on features of the mosquito.
Yes, please.
And once you go to the DNA, you cannot.
Yes,
you've not
please.
gotten there yet.
Yes.
Yeah. Thank you.
Thank you very much.
Thank you so much, Alice. You are discharged.
All right. Thank you very much, Alice. So our next presenter. So this is going to be an online session. Thank you very much, Alice. Our next presenter. So this is going to be an online session. Okay. Should I continue? All right. So we'll take our next presentation from Millicent Opoku. And next presentation from Millicent Opoku. So she will be presenting on the population genetics analysis, reveals source population of Simulium blackfly invading urban settings in Ghana. The population genetics analysis reveals source population of Simulium blackfly in urban settings. Yes, we can. Millicent, we can. Yes, Millicent, please go ahead. We are ready for you.
But on Simulium. So this will be a background. This will be an outline of my work. Background, rationale, aims and objectives. So this will be a background. This will be an outline of my results and then future directions. Simulium blackflies are hematophagous. Like I said, they feed on humans, animals, and so they carry a lot of pathogens. And one important pathogen that they carry is the Onchocerca volvulus, which is a nematode that causes blinding. And this is referred to as river blindness due to the association of the adult flies with fast-flowing rivers. So upon multiple bites of these black flies, they inject microfilariae into humans, and these microfilariae migrate to the eye, and then their death cause inflammation, can also cause skin depigmentation. There's also epilepsy or Northern syndrome reported in some parts of East Africa. And then these juvenile worms will grow into adults and form nodules that are clusters of female and male or female worms in the skin. And this is a diagnostic stage as well. And so that's why black flies are very important to talk about. And so this disease, it's very prevalent in sub-Saharan Africa with 34 countries affected. And 1.15 million people are blind, with 14.6 people with skin disease. The disease is present in Yemen and then a bit of Brazil and Venezuela. So this is the map of the prevalence. And so where you have very bright orange is where you have high prevalence or high transmission going on. In Ghana, the prevalence stands at 12% as at 2018. This data is quite old because we don't really have like a lot of data on this disease, and most of the prevalence studies are done in patches. Few research groups are focusing on this. That's why we need to talk about it. And over 4 million people are at risk as at 2023. The control has been vector control using helicopters to spray large stretches of rivers. And then when ivermectin was licensed, we couldn't use helicopters again because they were quite expensive. So now the mainstay is using ivermectin. So combination of these control measures has resulted in a decline. So you see this map, most of the orange patches have reduced. However, we still see some orange spots. And I must say that these control, the drugs have been given to people for, in some countries, they've had it for nearly half a century, and yet the disease still persists. What are some of the causes? So some of the major challenges to elimination of this disease are, so when you look at Ghana map, you see some orange, yellow, and then green. The green areas are areas with low prevalence, or let's say no high infection. And then you have a yellow, which has moderate infection, and orange, which still has some persistent transmission or hotspot areas. And so when you look at this, you can see that boundaries are not clearly defined. And so these areas are connected. And so if they are connected, what does it mean? One major thing that comes to mind when we talk about onchocerciasis transmission is humans moving parasites, and then black flies also moving parasites. And so tracking human movement is quite difficult, and sometimes your research will be limited by recall bias because sometimes the people want to say what you want to hear. And so my work mainly is trying to look at black flies moving parasites to places. And so you can have instances where they are moving it from orange to green areas or vice versa, or a fly that is uninfected from a green area moves to an orange area and then carries it. And one feature of this fly is it can fly up to 20 kilometers, and when assisted by wind, it can go up to 500 kilometers. And so when we look at this map here, I mentioned that it's associated with fast-flowing rivers. And the map of Ghana has a lot of river network system. And so all these areas are potential for black fly breeding or the disease transmission. But then in Ghana, it's estimated that all the 15 regions except Greater Accra has onchocerciasis. But then the story changes. In 2023, there were reports of black flies invading some parts of Accra. I think there have been sporadic invasions in some other parts of Accra. And so we sought to investigate this using the black fly, because we can easily go collect black flies. And so black flies, we are wondering where these black flies are coming from that are invading the Greater Accra. And so to do this, we are going to use genomics to track the source population. And to do this, I would use population genomics approach, first to identify the population structure and then assess migration between these areas that we are studying. And to assess the migration, there are two key important data that is needed, which is SNP data, single nucleotide polymorphism, or geocoordinates or GIS data. And so for sample collection, we used what we call human landed catchers. Those who do mosquito work are quite familiar with this, but then with black fly collection is quite very technical because you have to know how to hold the tube so your black fly after collecting does not fly away. And it took a while for me to grasp how to do this. And so after black flies are collected, they are kept in ethanol and then sent to the lab for processing. And so when these black flies are brought, I did DNA extraction using a spin column method. And so these DNA that were extracted, I did library prep and then whole genome sequencing on the NovaSeq X. And then generated short read sequencing, Illumina short read sequencing. And so with the data, there are some cleanup steps that you need to do, and then you map it to, I mapped it to a draft assembly that one of my colleagues generated. And then did haplotype calling and then genotype calling and then filtering of the data. And then these were imported into R for further data manipulation and visualization. So the results here. So first, I have a map on the left which has colors. So these colors represent where the samples were collected, and these colors are also going to run through all the analysis that I'm going to present here. So this PCA shows the similarities that we have within the sites that we collected the black flies from. The black flies were collected from 5 sites, 1 in the eastern region, 2 in the Volta region, Alabano and Holuta, 2 in Greater Accra, Paradise Valley, which is sort of on the fringe of the eastern and Accra, and then Termine, Boga Town. And so these samples were collected from 2022. So Esoya was the first collection we did because we knew there were black flies there. So 2022, we did some collections. And in 2024, between 2023 and 2024, I received samples. And so these samples were collected in 2023 and shipped over. So the genome analysis doing the PCA shows each dot represents an individual black fly. And so with my cursor, you can see that the group from here are from this side, the Soya and the Greater Accra side. And then you have what we call the Volta region. And so the Volta region sort of splits into 2. So there's 1 here and then 1 here. And so what we see is the further apart the points are, the more dissimilar they are. So those dots that are closer together will say they are very identical or they form 1 genome. And so based on this, we identified 3 distinct clusters. And so the flies from Accra were very different from the ones from the Volta region. And so further analysis, looking at the discriminate analysis of PCA. So this shows how the point or the individuals are interacting. And you can see that in the eastern region and the Greater Accra, there seems to be some interaction going on. And then the Volta is sort of separated with its own interaction. And so when we look at the admixture plot on the right side, you can see that there's mixing in some populations. So this shows that if, for instance, on the admixture plot, when you look at the left side, where you have the red and then the purple and then the blue, you can see that these are sort of one population or they are interbreeding. And so they are capable of forming one cluster of population. Here we'll call them molecular operational taxonomic units because we are at a point where we are using them to sort of help us in disease surveillance and monitoring. And then the Volta region, you can see that some individuals are also a mix, and then some are very distinct. So these 2 or 3 individuals are very distinct, and these are from Alavano. But then the rest are a mix of Alavano and then Holuta. So this basically shows you the mixing of the genetic material, and this shows that probably they are interbreeding. And so they are exchanging genetic material. And so with this, to further investigate, I did a landscape modeling and employed a method by Petkova, which is published in Nature Genetics. So he used an estimated effective migration surface model analysis. And what this does is an isolation by distance matrix. And so you expect that the further the points or the individuals are from each other, the more dissimilar they are. And the closer they are, the more similar they are. And so it uses geocoordinates and plots it on a polygon. So it draws a boundary around the area that we collected. And so here you see the blue areas. This blue here represents this. And so looking at how close they are, it's not surprising that they are mixing or they are very similar to each other. And as you move across, it becomes brown, light brown. And so you can say that there isn't any mixing or there isn't any effective migration along this path. And then on this path, there seems to be some mixing, but then it's not so strong compared to what we have down here. And so this brings me to this model that I made. And so you can see that a lot of flies are possibly moving from Esuoya into Paradise Valley, because initially I said we had reports of black flies around Paradise Valley and termite Bogota around that time. And we wanted to see where they were coming from. And so with the population genetics analysis that we did, showing that the genetic components or the SNP data are very similar to Esuoya, we conclude that these are probably coming from Esuoya. But then across these, and we can also say that we know that there's also the water lake, or there could be some barriers that are preventing these flies from crossing over. And so there isn't any mixing across this side, and there's so much separation, and then weak migration along this path. And so the invasion, we conclude, is driven by Esuoya, so we've caught the culprit. And so how does this come about? So in the past, these were how the water bodies were looking at. But now when you travel to most parts of Ghana, you see this. And these are as a result of mining activities. So we are thinking probably changes to environmental or the ecology, like it was mentioned last during yesterday. A lot of the presenters stressed on modifying environment and what the implications are for disease transmission. This therefore means that in as much as we are thinking the disease is restricted to other parts of Ghana but not to Greater Accra, this clearly shows that there's a potential for these flies from extending their boundaries. And so there's an increased risk in areas where there were no transmission. And so this raises a lot of issues as to how the surveillance and then control are being targeted. The need for control to be extended to other areas is also warranted. And so in summary, this genetic data helped us identify distinct clusters. And we also identified that the invasion was from Esuoya. And then we also show how we can use genetic data to show gene flow between sites, and also the potential of changes in our environment, the consequences and what the implications are for disease transmission. In future directions, I want to explore more resistant surface analysis, but in this analysis, I intend to incorporate environmental data, because we know that the disease transmission or the black flies are influenced by water, temperature, and then some vegetation. And so in our model, if you are able to put all these variables in, how will predictions look like in, let's say, 30 years? Can we predict in the near 5 years? And this will help us target our control so that we can reach our elimination goal faster than anticipated. And also, like I mentioned, this will help us inform surveillance and the control of onchocercasis. And then in future, I intend to identify whether there are adaptive genes that help these black flies survive in urban settings. It is said that it takes a whole village to do a research. And so I would like to thank my funders and the village that helped in bringing this work together. The heroes that did the fly collections with me, these are the fly collectors. I can't mention all their names, and so I put them here. The chiefs and elders, and then the disease control officers. And to my team in Ghana, Prof. Boache, Dr. Frimpong, Dr. Selassie, and everyone who has helped in ensuring that this work goes on smoothly and I get samples. Thank you. Thank you. Thank you. Yeah, now I can hear you on the Zoom, on the Teams.
It's either we are not interested or we didn't get it or we are hungry. Yeah, you understand everything. Oh.
Someone is asking questions I can't hear.
Okay, so Millicent, there are no questions for now. They said they understood everything. You are that good a teacher, yeah. Millicent, you can throw one question. You can throw a question. There are no questions from the audience, so maybe if you have a question for us.
Oh, I would say thank you to the organizers and for having me. And I hope that there will be a place for other vector-borne diseases. And so very soon we hope that the name may change to Pamca or, yeah. What I have to say, so we can be part of this community. Thank you.
All right, thank you very much, Millicent. Oh, a round of applause for her, please. Yeah. So, by way of recommendation, Pamca should be what? Pamva. Okay. Yeah, I think that would do.
Thank you. So, we are going to take the last presentation for this session, and it's going to be done by Bernard Osei. He'll be presenting on mathematical modeling of blood feeding and resting behavior preferences of indoor Anopheles mosquitoes. So you have the floor, Bernard. Thank you.
Thank you. Good morning, everyone. I must say that there is a little bit slight modification to the topic. Initially, we're looking at the mathematical modeling of this research or study, but then our model currently now going through on mathematical proofs to check the stability and other things of that. But having said that, what I'm going to present will not be different from what we sought to do or achieve. We're basically trying to, again, use statistical model, which will go into our mathematical model that we are trying to build. And so I'm presenting on optimizing indoor vector control, modeling blood feeding, and then the resting preferences of Anopheles mosquitoes. And these are my colleagues and my supervisors in here from Department of Mathematics, University of Cape Coast, and then Imperial College, and then Binary as well. Okay, so imagine you find yourself in a room where you have IRS being deployed and then bed nets also in place. But then you still have mosquitoes either biting you or flying around. In your mind, you think that, okay, that is the ideal that these interventions will either kill the mosquitoes or serve as a blockade for them. And we also know that mosquitoes also rest on various surfaces, which comes with different microclimatic profiles. And so you would tend to classify this as a mosquito behavioral adaptation, which in most research we can say that is a resistance. But here we want to call it as a behavioral resistance to this. And so this situation kind of very important for us to understand the behavioral preferences of these mosquitoes in order to improve our vector control strategies that we have in place indoor. So there is persistence in terms of transmission, because what we are thinking of is to look at how we can translate this behavioral adaptation in terms of transmissions when it comes to malaria spread. And so we are looking at the behavioral adaptation of these mosquitoes based on the rest-feeding selective preferences vis-a-vis the impact of climate change on malaria as well. So with that leads us to have a key question that we sought to look at in our model. That is, how does microclimatic factors such as temperature, light intensity, and relative humidity affect mosquitoes' selective preferences for resting indoor? And for the purposes of this presentation, we are seeking to find out what environmental factors influence indoor mosquito resting site temperature. And so you have in this diagram, what we sought to do is that our data, we collected data on various surfaces that mosquitoes rested on in the rooms, and we classify these surfaces as R1, R2, R3, R4 in our models, in our mathematical model, the original one. And then whenever you see R1, that is natural material surfaces, means these are materials that are made of natural things, wood, bamboo, and coconut fronds and others, textiles and fabrics. We have man-made hard surfaces and then leather material surfaces. So the study area and then the model, we considered 6 villages. We collected data from 6 villages and across 3 regions, that is Ashanti region, Greater Accra, and then the Central. And the data was collected between the period of 6 a.m. and then 9 a.m. And what we did was that we used torchlight and identify locations where these mosquitoes are resting. And then we used a multimeter gauge to mark where we collect the mosquito, put a multimeter gauge there, and then measure this microclimatic ambience of those locations. In analyzing the data, what we did is was to build a normal regression model, but then to capture for variations, we extended the model into looking at a mixed effect model. And then further again, instead of dealing with the frequentalistic approach where we have a one value or estimate for our parameters, we shifted to the stochastic approach where we use the Bayesian regression model, but then capturing variation as well. And so what we have here, okay, good. So what we have here is our Bayesian regression model, and we have our Y dependent variable, which is looking at the mosquito resting site temperature. And then we have our covariate, where is the temp indoor. This is the temperature measured indoor in the room, the overall temperature that we can have. For instance, when you come into this room, what is the overall temperature that we can find here? That is that. And then the Y variable is the temperature where the mosquito was resting. So that is the distinctive difference between those two variables. And then we included humidity and then light intensity, and then also distance from the nearest wall. Where the mosquito was resting, what was the distance to the nearest wall? Because we have that, okay, we apply IRS mostly on walls, so we included that. And then we capture a variability based on the day levels, and then this is the model residual error for that. And so these are the explanations for those done. And then as part of the study, we also try to see if we can use satellite, temperature that comes from satellite. So we got temperature satellite, values for that as well, and try to look at the differences in terms of variability for this. So in analyzing our data, what we did first is to explore the data to see some kind of trend across each surfaces in terms of having the mosquito resting site temperature as against the indoor community temperature that we have. And across each surface, we could see in each villages, we could see some trend in terms of the indoor temperature vis-a-vis the mosquito resting site temperature. So as the indoor community temperature increases, mosquito resting site temperature also tend to increase in across the villages vis-a-vis the resting surfaces that we had. So this was plotted with that. We did similar for the satellite temperature as well to see that, and you could see that there is no much increasing trend, but then kind of plateau on certain temperature levels for the resting site where the mosquitoes was resting. And so we went ahead to look at the variabilities among these key temperature, because we need to have a baseline between the resting site where the mosquito is resting, where the mosquito was resting, and then the overall temperature between the temperature that comes from satellite and then the indoor temperature. So we test that using the median absolute deviation to be able to quantify the variability or the distance between the two. So this was done using the community indoor temperature vis-a-vis the mosquito resting site temperature, and then we find the difference, and then we plotted that across various surfaces, and then we find out that yes, this was significant, telling us that the temperature difference across each surface was significant. So we went ahead to do the pairwise comparison between the surfaces, and we could see that here NS means non-significant, and then we could see that surface 1, which was natural material surfaces, and then surface 2, which is also textile and fabrics, there is some significance in terms of the temperature differences with regards to the community indoor temperature. This was for the satellite temperature, and we have the variability of plus or minus 2.2 degrees as compared to plus or minus 1.2 degrees. This is telling us that if we use temperature from the satellite as compared to where the mosquito is resting, there is more variability compared to that. And we went ahead to fit this with both covariates in our model to see which of them fits the model well. And it turns out that the community indoor temperature that we measured fit the model well compared to this. This was not statistically significant in the Bayesian model as we did. And so I presented, so here we have the model for where we use the indoor temperature, the community indoor temperature in the model. And we could see that there is a strong evidence for relative humidity and also community indoor temperature, that whenever there is for every increase in that, we see an increase in mosquito resting site temperature. Interestingly, this also confirms with what previous presenters have presented. There is also a negative decline in terms of relative humidity. So there's a how do you call it? Notably evidence on mosquitoes resting in what cooler surfaces, right? So we have that as humidity increases, mosquito tends to rest on what cooler surfaces. And also, like we mentioned, we have a variability components of our model, and we state our between day-to-day variability, which we try to capture in our model. So this, we look at trend for each of the covariates. Here, the trend here, we captures the variability as well in that. And like I explained in the previous slides, this explains it pictorially for us to see. This is relative humidity in percentages. So as relative humidity increases, mosquitoes tend to rest at areas where there is lower temperature. And that there is also light intensity. You could see that the confidence credible is much larger. When you go to the previous slides, although this is important, but it doesn't explain much to that in terms of where the mosquito is resting. And so in conclusion, what we conclude on is that mosquitoes tend to experience high variable temperature at where they are resting. And so there is no simple relationship or model that we can use to establish this relationship. But then on a median term, mosquitoes tend to rest at locations where we have 1.2% temperature difference across resting surfaces. And then we have that we cannot use thermal performance curve models in predicting where the mosquitoes are resting because of the variabilities that we have, and so we need to capture these variabilities in them. Again, also humidity tends to create a favorable conditions for mosquitoes to rest. And so these insights kind of support and that when we incorporate microclimatic monitoring system or routine system or surveillance into indoor residual spray strategies, we'll be able to account where mosquitoes tend to rest. And so the whole overview of this project is to look at each of the microclimatic attributes or features and then use that in our mathematical model to be able to predict the transmissions, malaria transmission across that. And so these are our institutions supporting us. These are my supervisors and my colleagues. We have Imperial College, Aconvic, we have CRED, and then University of Cape Coast. And then this is the mathematical model that we are trying to build and develop using that. It's quite complex because each of the microclimatic ambience that we talk about is also going to become as a function of itself and then being deployed in a differential equation to solve. So thank you for that.
Thank you very much, Bernard. So we'll take 3 questions from the audience.
Thank you very much for your presentation. I wanted to ask, before you started the presentation, you mentioned there was a change in the title because I was looking for how blood feeding or the correlation between blood feeding and their resting positions, but I didn't see anything like that. So probably was the reason you mentioned there was a change in your title. And I also wanted to find out if you considered seasons because I'm sure seasonality would also alter the microclimates of where they would prefer to rest.
Okay, so in our model, the model we've developed, the mathematical model we've developed and we are proving and testing, we've not captured seasonality into it as at now. Once we are able to prove without seasonality, we can look at how we can incorporate seasonality in terms of that. But here, what we want to do in terms of using the microclimatic ambient profile is that with those that has been measured during data collection, we want to see how that can impact that model. Because what I presented is more like trying to estimate the parameters that we will need inside our model. And so we are going to use those climatic, features to be able to predict, use that to predict transmission over time.
All right, thank you very much. So at some point you said you were using satellite temperature data. I want to know why satellites and not maybe some ground observations. So maybe you could have gotten data from, say, Ghana Meteorological Agency, which, for example, can say help us understand. So if you were using satellite data, why satellite, and which of the satellite data you were using?
Okay, so what we did was that we initially, when we were collecting the data, we collected the room temperature, the overall room temperature itself, and then in analyzing, we realized that okay, we need, if assuming that you don't have, you just collected the data with that, without having the overall room temperature, is it are you able to use temperature that is being collected from satellites? All right, and so that is why we sought to also have the temperature that comes from the satellite as well. So not that we only use the satellite temperature, but again we already had the data on ground, that the temperature on ground, and then also the temperature data, just to have the comparison between that. And then with regards to what type of satellite we use, I think we use the name have escaped me, but we use I think either CRID or LMEV. There's an abbreviation that we have, but I can always check that and give it to you whilst we have lunch or something. All right.
I wanted to find out, did you also consider areas where they've deployed the IRS embed nets to areas where there are no control interventions? If it's going to definitely affect them, even if the conditions are favorable for them to rest, it might still affect them resting in or out.
Yes, so one of the key things that we thought of was that in certain rooms there were interventions, and then other rooms there were, during data collection there were no interventions in place. And so one of the segregation or classification we intend to do is to have the model predict that, okay, if there is no intervention in place, how are we going to have those estimates influencing our model? And if there is intervention in place, how is that also going to affect our model? And so this is also a work in progress that we are looking at. So we have all that in mind, and then we are going to cater for that as well.
Any more questions? I think that should be it. So thank you very much.
All right, thank you.
So we've come to the end of the session. Sorry. Okay, right. So we've come to the end of the session, and because time is fast spent, we want to go for our coffee break, and then we'll come back and then continue with a student table talk. Thank you so much for your attention.
Please, coffee break is for 30 minutes so that we can come back and do the table presentations. You want me to reduce it?
Okay. So please, I hope the students are around. Thank you, Daniel. So as Daniel said, our next session will be student table talks. So as per the program, each student has been designated 3 minutes for this talk. So I hope you make sure you are within the time allocated. So for our first student, we have Juliet Adoma. I hope she's here. Yeah, okay, so you can start with your presentation.
Good afternoon. I'm Julia Sadoma from the Infectious Disease Epidemiology Research Group at KCCR, and I'll be presenting on insecticide resistance of Culex mosquitoes in Cape Coast. Mosquitoes are known to transmit various significant disease-causing organisms, including viruses, protozoans, bacteria, and nematodes. Culex mosquitoes are the most common mosquito species in urban tropical area and are major vectors for arboviral disease, posing a global health risk. Despite their role in transmitting severe diseases, little knowledge is known about their insecticide resistant status as compared to their malaria vectors. Therefore, this study seeks to assess the insecticide resistant status of Culex mosquitoes to 3 WHO class of insecticides in Cape Coast. The study was conducted in 4 selected localities within Cape Coast. Culex breeding sites were identified. Larvae was collected and brought back to the lab to be reared to adults under favorable conditions, that is for temperature 27 plus or minus degrees Celsius, and for relative humidity 70 plus or minus 20. Larvae was fed on fish meal and emerged adults fed on 10% sugar solution. 3 to 5 day old non-blood fed mosquitoes were used for the susceptibility test. 4 selected insecticides were used for this test, that is bendiocarb, deltametrin, phenetrotin, and primifos metal, with their respective concentrations. 24-hour post-exposure, mortality was checked and recorded. The Culex mosquitoes group used were resistant to primifos metal, deltametrin, and phenetrotin, but was susceptible to bendiocarb with a percentage mortality of 98.95%. The insecticide-resistant pattern for deltametrin aligns with that of the insecticide-resistant pattern for deltametrin in a Culex study in Cape Coast and for an Anopheles study in Kumasi. In conclusion, continuous monitoring and rotation of insecticide classes are essential for maintaining efficacy and preventing resistance. Thank you.
So, do we have any questions for her? No. Okay. So, for the next presenter, we have Jeffrey K. Boateng. I hope he's also here.
Hi, good afternoon. Today we'll be looking at the role of gut bacterium, Serratia massicens, on insecticide resistance. And I think across presentations from yesterday, a very peculiar keyword has been cutting across in this room, that's insecticide resistance. And then it's quite interesting that the fight with these malaria vectors, it looks like the human race, we are losing it. And so in order to redeem ourselves, we need to find some innovative measures to control these vectors. And in so doing, I think in recent years, there's been an upsurge in mosquito microbiome studies, highlighting the role of the mosquito microbiome in some phenotypic traits exhibited by the mosquito. But then there's still a pinch of information highlighting whether these mid-gut interactions could actually mediate insecticide resistance in mosquitoes. So then earlier this year, there was a paper that stated that exposure to a particular gut bacterium actually confers resistance in Anopheles gambiae mosquitoes. So here in the mosquitobiome lab, we asked ourselves, can our favorite bacterium, that's Serratia marcescens, confer resistance? In order to put that to test, we had to investigate whether some key genes involved in the detox pathways would be upregulated upon increase in the bacterium concentration in the lumen of the mosquito. And with the experimental procedure, we exposed the mosquitoes to 2 concentrations of the bacterium solution through a sugar mill, and then expose them to, challenge them with insecticide, particularly the deltametrin, according to WHO protocols. And after an hour exposure, we harvested some pooled intrazole for downstream molecular analysis. So then with the results, we could see some relative expressions of some key genes involved in the resistance, with the glutathione S transferase being the highly expressed across our experimental groups. However, because our objective was to investigate whether an increase in the bacterium would actually be an influence on the expression of these genes, we realized there was no significant impact on an increased bacterium in the gut. And so in conclusion, we can boldly say this particular bacterial stream didn't actually induce the expression of some key genes involved in insecticide resistance. However, in order to make a good claim that this particular strain, it's a very effective biocontrol tool, we would have to adapt transcriptomics in order to investigate some other key genes involved in insecticide resistance as they would be expressed upon exposure. Thank you.
Thank you, Jeffrey. So for our next presenter, we have Hilary Ansah.
Good afternoon, everyone. My name is Hilary Ansah from the Infectious Disease Epidemiology Research Group from KCCR Kumasi. I'll briefly be presenting a study on optimization of the direct membrane feeding assay to assess the infectivity of Plasmodium falciparum parasite to Anopheles gambiae vectors in Ghana. So the DMFA, as we all know, is a widely used tool when it comes to studying malaria research to assess how infectious humans are to mosquitoes. However, the outcome of the DMFA can be unreliable when the gametocyte loses its viability during sample collection to the transportation. So in our study, we aimed to optimize the DMFA by improving the sample handling and also improving storage conditions during the sample transportation. So this was a cross-sectional study conducted from August 2021 to January 2023 across 4 Ghanaian communities. We recruited asymptomatic individuals aged 4 to 15 years with no sign of fever or anemia. Gametocytes samples were taken for the detection and confirmation of gametocytes. Once this was confirmed, heparin blood samples were taken and then sent to the KCCR entomology lab in the portable incubator, where the blood was given to the mosquitoes using the DMFA setup. 7 days post-infection, the mosquitoes were dissected for the detection and quantification of oocysts in their midgut. So after our first set of experiments, we observed lower mosquito infection rate, hence the need for the optimization. So for the optimization, more focus was placed on the distance from the study site to the entomology lab in KCCR, and also we improved how we handled our samples, and we tried to limit the opening and closure of the incubator to minimize the fluctuations of the temperature in it, which could affect the infectiousness of the gametocyte. So to our results, we observed that with the optimizations that we put in, it significantly increased the mosquito infection rate. And then to the dynamics, we observed that males and older children, that's children between 11 to 15 years, recorded higher parasite prevalence, However, the parasite density was seen to be higher in the younger children, that is 6 to 10 years old. And then also, samples from females and younger children, that is 6 to 10 years, recorded higher mosquito infections and intensity as well. Parasite prevalence was also recorded to be higher in the rural communities as compared to the peri-urban communities. So in conclusion, we can say that with our optimization to the DMFA, Plasmodium falciparum gametocytes can remain infectious for up to 4 hours, thus making the DMFA very feasible in even remote field settings. And also, we found that gender, age, and gametocyte density were found to be positively associated with the success of parasite transmission to mosquitoes. Thank you.
Thank you, Hilary. So next we have Jima, Ibrahim K. Jima.
Okay, so hello everyone, good afternoon. Jim Ibrahim. So I'm looking at the effect breeding water has on insecticide susceptibility of Anopheles gambis and Selato during laboratory colonization. So during the formulation of insecticide resistance, it is imperative that vector control researchers expose these novel formulations to insecticide resistance mosquitoes. However, these mosquitoes tend to lose their resistance status within the laboratory setting. So this study looked at raising these mosquito colonies in 3 different breeding water sources, where we look at the field water, where they are raised in the where they are in the field, in the wild, tap water, and distilled water. So for this very study, we sampled these mosquitoes from Opebia, which is a vegetable growing farm within the Accra metropolis, and was raised for 11 filial generations in the laboratory for the 3 colonies, that is the tap water, field water, and distilled water. And for each colony, for each filial generation, they were phenotypically assessed using the WHO susceptibility assay against the pyrethroids, organophosphate, organochlorine, and carbamate classes of insecticides. We also conducted a synergist assay using the pypyrenol butoxide, that's PBO. And mosquitoes from these assays were sampled and screened for the knockdown resistance mutation and acetylcholine esterase gene mutation. Mosquitoes directly from the insectary were sampled and screened for the metabolic enzyme activities of mixed function oxidase, the esterases, and glutathione S transferase. Since this is a breeding water sort of study, we sampled some from the insectary directly and screened them for various parameters to see whether it has an impact on the survival of these mosquitoes as well as an influence on the resistance status of these mosquitoes. So at the end of the study, it was known that the breeding water actually has an influence on the survival of these mosquitoes. And to replicate and maintain the same high resistance of these mosquitoes, the study actually suggests that these mosquitoes should be raised in the field water, since the tap water colony and the still water colony were only able to maintain just the phenotypic and genotypic resistance mechanism. So interested individuals can pass by our poster, that's ABS 62 for extensive discussion on this study. Thank you.
Thank you, Jima. So next we have Ruby Awoka.
IT guy. Can we do the next one and then she'll do hers last?
Okay, so the next one is Sally. S. Nuruddin. Nuruddin. Selma.
Good afternoon, everyone. So I'm Selma Sally, and then I'm looking at tick and tick-borne pathogens in canine hosts in Ghana. Tick surveillance activities in Ghana have mainly focused on livestock, and there's been results for diverse tick species and tick-borne pathogens of zoonotic importance. However, there's a critical gap in dog population, which can be used as sentinels for monitoring the tick-borne pathogens in our environment. My study is looking at identifying tick species in dogs and tick-borne pathogens they harbor. So far, ticks have been collected from dogs in Ashaiman, Oponglo, and Kumase, and these have been identified morphologically. Most of these ticks were identified to be Rhipicephalus sanguinus. Upon further identification using molecular methods, we identified some as some other species as Rhipicephalus linnae and Rhipicephalus leprus. There's also been identification of Amblyoma species as well. Upon further screening of these tick species for tick-borne pathogens, we identify Rickettsia species and Coxiella benneti. These are zoonotic pathogens. They've been identified already in Ghana to infect humans as well. We also identified Hepatozoon canis and Escherichia canis. These are dog pathogens, but they can also infect other domestic animals. We also identified Candidatus anaplasma cameli. This bacterial pathogen normally infects camels, but in this case was found in a dog. It could mean that the dog came in contact with a camel, or this bacterial pathogen is also spreading its host. So based on my findings, we can conclude that domestic dogs can be used as sentinel animals to monitor tick-borne pathogen transmission in Ghana. There's also a need for frequent surveillance and public education to ensure owners to protect themselves from infections. Thank you.
Thank you, Selma. So we go back to Ruby. I don't know.
Hello, good afternoon. My name is Ruby Aoka from the University of Cape Coast, and today, thanks. So today I'm happy to share with you with my project by using mathematical modeling to assess new intervention control tools that we have. And okay, it's working. So as Ghana targets to eliminate malaria in some 21 districts in the Greater Accra region, and with the current control tools that we have, that is the ITNs, that's the insecticide nets with the IRS that we have. From yesterday to today, people are already talking about resistance, like vector resistance to all these things. So what can we do? And the outdoor biting, even if we are able to have an effective insecticide that can combat these vectors, but all of these two control tools are targeting indoor biting rather than outdoor biting. Hence, there is the need for us to look at another novel tools that can complement the already tools that we have. And that is the attractive targeted or toxic sugar bait that we have. And with this attractive targeted sugar bait, it is something that will be exploring the mosquitoes, the sugar feeding of the mosquitoes. And with that, when mosquitoes feed on this sugar solution, and with this sugar solution, we've made it like toxic. That's when mosquitoes should feed on it, they die. And with that, it depletes the mosquito density, and enhance, if the density of mosquitoes are reducing, the transmission also reduces. So that is the knowledge behind it. Okay, so with this, we are using a mathematical model to do it. And with that, we have these two assumptions. Does the mosquito sugar feeding, does it depend, or it is independent of the blood feeding cycle? So we are trying to explore these two aspects to do our work. So let me see if this will work. No. Let me still use this. So with this, then we have the mosquito compartment from the susceptible to the latent or the exposed. So when mosquito bite an infected person, they become exposed. But with this compartment, doesn't mean when they bite an individual and host, that person can be infected. But they'll rather going through an incubation period. After that, they become infectious themselves. That's when they bite someone, they can transfer the parasite to the person. And mosquito can move from this compartment to this compartment when they feed on sugar bait, and we use FS as the sugar feeding rate. So they will move to this compartment. And with our model that we are going to do, we are using a 7-year, like a period of 7 years. And we are saying that our ITN usage, but this is by the DHS, the demographic survey report, that 35.2 people use the ITN in Greater Accra region. And we also have, like, even though IRS is not used in Greater Accra region, we are trying to give a 60% coverage of it. And we are saying we will be using a different kind of sugar bait feeding, like proportions, to evaluate the effectiveness of this model, the ATSB. So let me move. So with our findings, you could see this is when ITN, and ITN was introduced in the first year, and you could see the reduction in prevalence. And as time goes on, we introduce the ATSB at the 4th year. So at the 4th year, when we have the feeding rate to be 0, that means no sugar feeding or bait feeding. Everything was normal, like the normal way the simulation was going on. But when it becomes like 0.04 or 0.2, you can see a greater reduction in the prevalence. And this is due to the independent. It means when mosquito sugar feeding is independent of the gonotrophic or the blood feeding cycle, we have a higher reduction. And if it is dependent, we don't see that kind of reduction in the prevalence. And at times, there is another one that I'll be happy if you really want to delve more into this. You see me at this poster stand, PG ABS 58, because with this, I did not show marginal gains are lower when IRS, because when you use effective like insecticide on mosquito, the ATSB tend not to work that much, and this also confirmed with other literatures. And I'll be happy you come to my stand and we all work together or like know much about my work. Thank you.
Thank you. Thank you, Ruby. Thank you all presenters for your lovely presentation. So we can also visit their poster stand for further deliberations. Okay, so next on the program, we have presentations from our platinum sponsors. So first on the list is Syngenta. I don't know if they are ready. Syngenta.
just 1 minute to introduce.
There's a button on this.
Thank you. So good afternoon, everyone. I'm Howard Diallo from Syngenta. We are an agribusiness company, but also a manufacturer of insecticide for indoor residual spraying. First of all, I need to thank Pamca Ghana for inviting us. Oh, you are not hearing me? It's better like this? Okay. So I was saying that I would like to thank Pamca Ghana for inviting us in this important conference where you have researchers, scientists, academics sitting together, even us, the industry, together to discuss about challenges, innovation in vector control. I would also like to thank you to give us the chance and the opportunity to introduce our cutting-edge technology in IRS. And I think, ladies and gentlemen, it takes almost several years, like 10 to 20 years, to develop new molecule with a new mode of action that not develop any resistance yet. So I think I'll just allow 5-minute presentation, so I will share a video who can explain better than my words what mode of action I'm talking about. So can we go to the video? Oh, it's not practical. To conclude, after, oh, it's good, okay. So to conclude, I would like to say that I'm pleased to inform you that these products, Sovrenta, have been PQ listed by WHO with 12 months of residuality. I think it's the first product in the world to get this kind of recognition from WHO. I would also like to add that I have my technical manager here, Robert Ba, who is taking some pictures behind on the back. So he's there with me. If you have any question on sovereignty, feel free to come to us. We have our booth there. We can try to answer your questions. If we don't have all the responses, we try to give it to you later on. So thank you for your attention. I think I'm not, it's good? Okay, thank you all, and thank you for your attention.
So, Memamo Aceh. Okay. Hi. Hello, everyone. So, at first, I wanna extend my gratitude to all of organizer and speaker and participant of this Pamca conference. And I'm glad to be here today. So, actually, this is my first time visiting in Ghana. It's Thank you so much. So my name is Toshiki Ohashi from Mitsui Chemical Crop and Life Solutions. I think it is a little long name and company name, so please remember me. My name is Toshi, and company name is Mitsui. It's very short. And Mitsui is Japanese R&D focused company that serves as global provider of services and top quality products to in the field of agrochemicals and pest and vector control. Today, I'm happy to introduce Vectron T500 that is innovative IRS products. And it is to tackle the issue of insecticide resistance for malaria. So Vectron T500 is a cutting-edge IRS product featuring tenebenal as its active ingredient. And it has a unique mode of action, providing a strong efficacy against resistant mosquito. Additionally, Vectron T500 is not only odorless and stainless, but also has a long residual efficacy on various kind of wall, more than 9 to 12 months. And it has already registered in Ghana and been treated on various areas in Ghana. So it's by cooperating with Agamal and QPest BOPP PMI since 2024. So taking this opportunity here, I would like to express our gratitude to all support. So regarding Vectron T500, that's pretty much it. So finally, I have introduced my company booth. So we have a company booth at this ground area, and we provide this note and this pen printed by Vectron T500 logo. It's free. Yes, and so thank you. And additionally, we provide Japanese chocolate. It's called Ghana chocolate. It is very famous and most of tasty in Japan chocolate. It's almost free. So if you don't get these items yet, please feel free to stop by our booth. Thank you so much, Medamo Ase.
Thank you, Mitsui Chemicals. Thank you very much. So next we have crop and life solutions.
That's the same one.
That's the same.
They do all of that.
Okay, thank you. So
oh, he's here. So EK Consult.
okay, so we have EK Brand Consult.
Good afternoon.
My name is Elom Foley. I'm the founder of EK Brand Consult. And just to give you an idea of what we are and why we are around such great scientists today. So we're a business development firm, at least that's how we describe ourselves. And then we use branding, marketing, and technology in order to maximize impact for the businesses we work with or the brands we work with. And we were excited about the opportunity to work on this project, which has been, in our opinion, very well organized. And we've provided the streaming services. Where we think we can help is in helping tell the stories that matter. And I think with a program like this, which we have learned from being here, that is critical in terms of the development of our nation and development of the great minds here. Part of what we do or we aim to do going forward is to help these programs like this grow, and it usually comes from documenting it properly, sharing the documentation with brands that can support and help maximize it. So my older sister is a researcher. She works on Lyme disease, so of course she's my parents' favorite child. And but I'll let my parents know that I'm part of a wonderful scientific community as well, and this is our little contribution. So going forward, if there's any other thing that you're working on where you need any support in terms of streaming, branding, storytelling, please feel free to contact us. We are based in East Legon, so we'll be more than happy to help in any way we can. Thank you.
Thank you, EK Brand Consult. So over to you, Daniel.
All right, ladies and gentlemen, this is the time where you can go downstairs and take a look at all the poster presentations that have been displayed, have discussions, ask questions. Also, you can network with each other. Thank you for sticking around for the student table talks. And lunch would be at 1:30. We would kind of come around and let you know when it's ready, and then we'll go ahead with that. The fourth scientific session would be at 2:40. Please come in here by 2:35, and then we'll start at 2:40. Thank you. Bye. Yeah, that's the one where... We're going to move straight into scientific session 4 with the sub-themes One Health and Integrated Approach to Vector-Borne Disease Control, Community Engagement in Disease Control, and Modeling for Effective Management of Vector-Borne Diseases. And that sub-theme is a continuation from a previous session. This session will be chaired by Dr. Kingsley Bedu, PI and lead of the Vector-Borne Infectious Disease Group at the Theoretical and Applied Biology Department at KNUST. Dr. Kingsley Bedu would be assisted by Dorothy Obobi, who is a PhD candidate at LMU Germany and UCC here in Ghana. So Dr. Bedu and Dorothy, you may move to the head table. So we'll go on and invite our plenary speaker, Dr. Seth Addo, to come and start the session with his presentation.
Okay, good afternoon, everyone. So I'm going to shift our attention from mosquitoes, from bedbugs, onto ticks. So there isn't really a lot of research on ticks in Ghana, but we've come together, a collaboration of people from Noguchi, from KNUST, from Navrongo Health Research Center, from Kintampo Health Research Center, and we are putting together surveillance activities to be able to look at what ticks are in Ghana and then what pathogens they are carrying. So the talk I'm going to give is focused on livestock ticks. So I'm going to give a talk on tick-borne pathogens in Ghana, looking at the complexities of epidemiology and then some public health implications. So worldwide, it's been seen that ticks are able to transmit pathogens that affect both humans and animals. So when it comes to human infectious diseases, those transmitted by vectors, mosquitoes are ranked first. When it comes to pathogens of veterinary importance, ticks are ranked first. And then ticks rank second when it comes to pathogens being transmitted from animals to humans. And it's been seen that worldwide, about 80% of livestock are affected by these ticks and then the pathogens that they carry. It's also been seen that about 75% of emerging infectious diseases have animals being a source of infection, and then we have ticks playing a key role in transmitting these zoonotic pathogens. So at each stage of the life cycle of a tick, with the exception of the egg stage, so the larvae stage, the nymph stage, the adult stage, they require a blood meal to be able to molt into the next phase. And in the process, they either pick up a pathogen from the host or give a pathogen out to the host. There are some pathogens that are transstadial or transovarial, so they will pass on from the mother to the offspring either through the egg or then from one life stage to the next. So then you realize that once a tick is infected with a transstadial or transovarial pathogen, it will remain infected for life, and then it would be able to spread it. So imagine if one tick is infected with, say, CCHFV, and then it produces so many offsprings. chances are it will pass it on, and then the infections will be spread across. So then, humans, in their bid to meet our nutritional needs, end up moving with their livestock across borders. And because our borders don't have a physical barrier, you can just pick your animals and cross over. So we have people coming in from Burkina Faso into Ghana with their livestock. And then we do not have surveillance checkpoints at these borders. So then once an animal is brought into the country and it's physically healthy, that's it. Even at the point of entry at Pamca-Gh, where we have imported livestock coming in, they just vaccinate for respiratory infections, and then that's it. So whatever ticks are on them, whatever pathogens they might be carrying, will end up coming into the country. So then it's easy for ticks to spread into Ghana, and then whatever pathogens they are having to also infiltrate us. And it is easy for some of these tick pathogens to be misdiagnosed. For instance, Babesia, when you look under the microscope, to an untrained person, it looks similar to malaria parasites. So that if I pick it up, I will assume it's malaria, but then it could be Babesia. And in our hospitals, we don't have systems in place to check for these tick-borne pathogens. They would most likely miss it. There's also the scarcity of data when it comes to tick-borne pathogens across sub-Saharan Africa. Although we are the ones mostly affected by these tick-borne pathogens, there aren't many surveillance activities going on, and we don't have measures in place to even prevent most of these pathogens spread. So then a lot of these small-scale farmers are really affected. And then we have a lot of these zoonotic pathogens also spreading. So in Ghana, especially up north, we realize that most of the inhabitants live with their animals. They end up breeding cattle, sheep, and goats, either to help them on the farms or to sell them. In the process, they get exposed to these tick-borne pathogens. If we're able to generate enough data from the tick surveillance activities, we'll be able to put together measures that will be able to help us prevent them from spreading. So why is there a need for us to even do tick surveillance in the first place? We realize that humans and animals are like the rest of these tick-borne infections. And to be able to protect animal and human life, there's a need to be able to do surveillance activities to find out what pathogens are even spreading to begin with, so that we know which effective measures can be put in place. In order to safeguard food supply as well, preventing animal loss, because some of these tick-borne pathogens can cause stillbirth in the animals, which would mean if you have about, say, 100 cattle, if they are unable to produce within a short period, you're going to lose out on all of them. It's also expensive to be able to treat these animals for some of these tick-borne pathogens. And so then, especially these small-scale farmers, they run at a very great loss. So then there's a need for these surveillance activities. We also need this, also to be able to help us safeguard human health, as I said, and also be able to control these tick-borne diseases. So we've been able to collect ticks from the Upper East region. We've collected some from Tamale, from Kintampo, from Kumasi, and from Greater Accra region. So we started off with a funding agency, GUICE, which usually targets military sites. And so we were limited. And then for my PhD work, I got a chance to sample from up north. And then we've had students also sampling from Tamale, and then currently students doing work from Kumasi as well. But then we've not been able to cover the entire Ghana. So then we have just some data, but the data we have so far is significant to show what tick species are circulating and then what pathogens they are carrying as well. Most of our collection methods has been through hand picking. We tried tick drugs, but then we realized that it wasn't getting us. We didn't actually get anything from tick drugs. So then we ended up sticking to just hand picking directly from the animals. So in terms of identifying the tick species, we collected ticks from cattle, sheep, goats, and then we started off with with morphological identification, so using taxonomic keys which are available. But then we realized that there are some species that are similar, and it's difficult to use morphology alone to distinguish between them. And then some of the tick species were also blood-fed, so they lose most of their physical features, so then it's hard to tell. So we had to rely on molecular methods. So did extraction, did PCR, and then with this Sanger sequencing to be able to know the exact species. And from the molecular sequencing, we've been able to identify new tick species which we didn't think were here. So for some of the tick species that we have identified to infect livestock, we have found Amblema variegatum, which is the only Amblema species we found infecting livestock. So there are other Amblema species in Ghana that infect wildlife, which has been published previously. But then for livestock, it's just Amblema variegatum. For Hyaloma species, we have Rufipes, we have Truncatum, and then using molecular methods, we were able to find Hyaloma marginatum and dromedary. So dromedary primarily infects camel, but then studies show that it's able to move on to sheep, even to cattle, and then sometimes goats, depending on how close they are with camel species. Hyaloma marginatum originally is supposed to be in the northern part of Africa, but then we are finding it here in Ghana. And so our guess is it's either it was brought in by migratory birds, or because we treat livestock a lot, it was brought into the country. So other tick species, we found Rhipicephalus sanguinus, Rhipicephalus tyrannicus, which is closely related to sanguinus. So then, using morphological keys alone, you would assume it's sanguinus, but then you'd have to use a molecular approach to be able to tell the difference. We've also found a number of Bufalo species. The one of most interest is Rhipicephalus microplas, which is an invasive tick species. And because of its high reproductive capacity, it's able to invade a region, multiply within a short time, and because it's resistant to most of the acaricides being used, you would apply and then you end up getting rid of all the other tick species, and this particular one would still thrive and be able to spread whatever pathogens it's carrying. We've realized that up north, it's usually Amblema variegatum that is the highest, but then when we come to the Greater Accra, it's Microplas that's dominating. Probably because here in Greater Accra, we use quite a number of acaricides, so then we end up getting rid of the other species, and then this one is thriving. So now looking at some of the tick-borne pathogens that are carried by these tick species, we've realized that all the tick species identified so far carry one or more zoonotic pathogens, which shows how important they are in the spread of these pathogens. Amblema variegatum, for instance, is the most predominant tick species infesting livestock in Ghana, and it's carrying 4 different zoonotic pathogens. So then imagine if their population keeps on increasing in Ghana, we would always have that high transmission rate of these zoonotic pathogens, especially Rickettsia africae, which is almost always the highest zoonotic pathogen we find when we screen these ticks. Another zoonotic pathogen of interest is the Crimean Congo hemorrhagic fever virus, which is CCHFV. Quite a serious pathogen that causes infections in humans. We've already found pathogen exposure in humans in the Kumasi abattoir, and then we found it in the tick species as well. Other zoonotic pathogens that would cause serious infections are Coxiella benneti. So it's more likely to be infected with Coxiella by handling an animal or an animal part, the body fluids or the blood, rather than a tick biting you. So then it means abattoir workers especially will be at risk of this pathogen. And from our sampling, we realized that in our abattoirs, they don't have a strict policy when it comes to protecting themselves. A lot of them use their hands to handle these animals and to slaughter them. So then they are really at risk of being infected by either CCHF or Coxiella benneti. For Rickettsia, it's usually through a tick bite. A new zoonotic pathogen which we found in Ghana not long ago is the Anaplasma capra. So this particular pathogen was first found in China to infect livestock, and then we moved to humans, and now it's in wildlife. And from there, it's spread across to multiple countries. So that we finding here in Ghana shows that these livestock trade, although it is good in terms of us getting these livestock into the country, they are also coming in with these tick species which have these pathogens. So then it goes to emphasize the need for us to have a robust surveillance activity that would be able to monitor these ticks and the pathogens that they are harboring. So then we had a chance to also pick samples from humans in Kumasi, in the Kumasi abattoir. And and we found 3 of them exposed to Rickettsia africae, Coxella burnetii, and then Rickettsia atzkimani. And these were they were healthy people, actually healthy people, and the sample was dry blood source from a finger prick. And that was enough for us to find this pathogen, the DNA of the pathogen in there. So then it goes to show that they are at risk of being infected. We also collected blood samples from healthy people across Ghana and screened them using the MarkFix. So it's an advanced ELISA which can detect up to about 50 different pathogen exposure in a sample. And we realized that these people were exposed to CCHFV, they were exposed to other vector-borne diseases like Red Valley, West Nile, and we had a lot of them exposed to dengue as well, which goes to show that even as we are there, we get exposed to these pathogens. And for most of us, we do not show signs or symptoms, so then we seem fine. But then we are not sure as to when an outbreak will happen, say from CCHFV. We've also realized that livestock, such as cattle, sheep, and goats, also harbor these zoonotic pathogens, aside from the pathogens of veterinary importance. And these livestock amplify these pathogens. So then if a tick attaches to it, it picks it up, gives it to the human either through a tick bite or the human handling the animal. Theileria ovis, for instance, is a pathogen of veterinary importance. It's known to cause serious infections in small ruminants. So it can cause stillbirth. Anaplasma phagocytophilum is also a zoonotic pathogen, primarily in cattle, but then it's been known to infect humans and other small ruminants as well. The new pathogen of veterinary importance that we found was Theileria orientalis, which hadn't been reported in Ghana before. Babesia species Lintan, which also wasn't previously reported in Ghana. And then there was another one, Babesia species Xinjiang. So these pathogens are usually, for some reason, most of them are found in China, or they originated from China, so then they were named by them. And then we realized that they are crossing over into these countries through the livestock trade activities that we do. So I decided to show this due to the importance of CCHFV, and it's so the segmented virus usually has 3 segments, the L, M, and S segment. To know how virulent the pathogen is, particular interest is with the M segment. Usually when this pathogen is replicating, it has a tendency to pick up genetic material from other viruses that it's co-infected with. So then, when it picks up this genetic material, the M segment usually changes. And in Ghana, we've been able to find 2 different strains of the virus. One with its M segments similar to other strains which are reported in genotype 3 Africa, which is the strains that infect countries including Ghana. And then we found another one with its M segments clustering with strains in genotype 1 Africa, which is supposed to be infections from Sudan, from Senegal, and then from Congo as well. So then we realized that 2 different strains of this pathogen are circulating here in Ghana. We found one of this strain reassortment in Kumasi, Abattoir. We found another one in the Upper East region. And it could be because of the livestock trade, because when livestock come in, they start from Paga, move through Navrongo, down to Kumasi, and then down to Accra. So now along the line, some of these livestock, especially cattle, are slaughtered, and some are also sold. So then we have these livestock bringing in these ticks and the pathogens. So then looking at the presence of all these ticks and all the pathogens that are in Ghana, we are at risk of being infected with African tick bite fever, which is caused by Rickettsia africae. Given the high occurrence, it's very much likely that we would be infected. And if any of us has been bitten by a tick before, there's a high chance we have picked up a tick-borne pathogen without realizing. And if we were to do a seroprevalence study on us, we might find some level of exposure. There's also the risk of CCHFV infection, Coxella burnetii infection as well. And there's also the high risk of anaplasmosis, theileriosis, and then ehrlichiosis. There's also that risk of we losing a lot of livestock, especially within our rural communities, especially to the small-scale farmers who really rely on these livestock for their survival. that will also lead to a level of food insecurity, and then we have a lot of these farmers losing their daily livelihood. So we realize that some of the risk factors in Ghana are occupation. So you keeping animals, you working in the animal husbandry, you coming into contact with the animal increases the risk of you being infected. Again, our lifestyle activities like hunting. In Ghana, we have a lot of hunting going on. Most of it is unregulated, so then coming into contact with these animals could lead you to be infected. And we realized that the pathogens being transmitted in Ghana seems to vary across different ecological zones. So the pathogen transmission in the Upper East region is different from what's happening in Kumasi and that happening in Accra. Also, climate change can have a serious effect on these ticks. Example being Rubicephалus sanguinus, which has been found to bite humans more when temperatures go up. So some of the control strategies being used in Ghana currently include acaricide use, which is effective, but then overuse of it will lead to acaricide resistance. So there are some campaigns here and there on how to avoid tick bites and how to seek early treatments, but it's still not enough. There's also the routine animal health checks by veterinary officers. So if the farmer calls in a veterinary officer, they'll check the animal and then they'll give advice on how to protect themselves. There's also surveillance activities which we are doing, but then we are restricted by funding, so we can't do a lot, but then we're doing significant surveillance. Some of the challenges is funding, and we are still trying to put together the infrastructure to do more surveillance activities. When you compare it to mosquito-borne disease, there's a lot of surveillance going on in there, but when it comes to ticks, it's more on the less side. There's also that lack of awareness, because most health providers don't even know about tick-borne diseases or what effects it can have on us. They are mostly focused on other vector-borne diseases like malaria. Insecticide resistance is also a big thing in the country, because most people use the acaricide as and when they feel the tick infestation has gone high. So then they don't rely on the veterinary officers. So then they use it indiscriminately, which is leading to acaricide resistance. We also do not have diagnosis facilities currently available. So then to do tick surveillance, you need a lot of reagents and a lot of PCR machines, which you'd only find in the research institutions. In the hospitals, they don't have the capacity to do that. There's also the environmental concerns, which comes with using acaricides, which will contaminate the environment and then could contaminate our water bodies if they leak into it. So for future directions or what we need in terms of research, we need to improve diagnostic activities. One way to go would be to use next generation sequencing, but it is quite expensive, so you need funds for that. We could also look into vaccine development to get vaccines to help protect us from being infected with these tick-borne pathogens. There's also the need for surveillance activities. One way to go is to use sentinel animals. In this case, we can use cattle, since they are the predominant animals. We also need to look at what impact it has on the society. One way we need to go is the One Health approach, where veterinary officers, health professionals, environmental agencies, research scientists all need to come together to collaborate and be able to find sustainable ways to tackle the effects of these ticks and the tick-borne pathogens. So like I said, there's a need for that partnerships. There's a need to build more capacity when it comes to tick research in Ghana. And also the need to raise some of these pathogens or these diseases caused by ticks when it comes to our national policies and during our meetings. So in conclusion, looking at tick-borne surveillance activities require all of us coming together. It's not just about the farmers, it's not just about the researchers, but it involves all of us coming together to be able to put in effective measures. There's also the need for us to use acaricides appropriately. One way we can go is to delve more into plant-based acaricides, which would be safer to use. And we can look at cattle as a great way of monitoring what ticks are coming into the country and what pathogens we can look at. So the partnering institutions are Noguchi, the Naval Medical Research Unit, Navrongo Health Research Center, KCCR, and Kintampo. So these are the team members in Noguchi who do all the tick surveillance that we've done so far in Ghana. Thank you.
Very, very wonderful presentation, highly relevant to national surveillance. We have time for 3 questions. 3 quick questions. Please be direct as much as possible, and then, yeah, thank you.
Thank you for the nice presentation. My question is concerns with the new species that appears to originate from, is it Asia or China? I want to find out if the genetic way confirms that that is where they are coming, or they were also found here, but it's just now that.
So that pathogen was first found in China. There's a publication to attest to that. But then for most of these pathogens, because we weren't looking, we're not sure how long they've been here. It's possible they've been here all this while, but because we didn't have the capacity to test for them, that's why we didn't find them.
Next question.
Okay, thank you. Please, my question is, when during screening or during collection of these ticks from various abattoirs in Ghana here, when you look at the Fulani heads, mostly the cattle breeding, did you also target such people? Because most of the time they don't pass through our normal borders.
Yeah, so in our collections from the Upper East region, we had a chance to sample from these Fulanis. And they were quite cooperative with us, so we were able to get quite a number of tick species, and then we saw some of these pathogens also with them. And they move across the Burkina Faso border a lot, so then they also end up contributing to the ticks invading us and then the tick-borne pathogens they bring into the country. Yeah.
Any other questions?
So when you were presenting, I didn't get something well. You were saying the abattoir workers were at risk. I didn't get it if they were at risk or they tested positive to some of the tick-borne diseases.
Okay, so I said they are at risk, and then some tested positive. So we've had a previous study which found some of them exposed to CCHFV. And then we found 3 different zoonotic pathogens also in the abattoir workers. So we have evidence for seroprevalence, and then we have evidence for the pathogen being present itself. And because they don't protect themselves when handling these animals and the parts, they easily get exposed. And then we had a student looking at, did a questionnaire, and then we realized that about 85% of them had been exposed to tick bites, which confirms they being at risk.
Yeah, sir, thank you. I have a question. I don't know to what extent you are actively engaging the public health division to come on board. Because if you say malaria, there is the national program for malaria and other diseases. This is something very really serious. I teach zoonosis, and I know Coxiella burnetii can cause spontaneous abortion in people. They may be going to church that some which is not preventing them from giving birth, but it is a zoonotic disease. I don't know how the public health division is coming on board to help. Have you engaged them?
So we haven't actually made noise to that level yet. It's something which is on the table, but we haven't actually moved it far. And Prof. Dazi is actually our PI when it comes to these tick surveillance, and we're hoping to move it from our research level to the policy level and be able to come up with how we can prevent these infections.
Okay, wonderful. Thank you very much for your presentation. Yeah, I think that's all of us scientists we have to do. Once we are doing something like this, highly nationally important, we should do our best to engage the government. Unless we have all done very well coming up to this point. Let's finish very hard. Let's invite Priscilla, a J. Kusi, PhD student from Infectious Disease Epidemiology, ACCR. Priscilla will be speaking on partial clearance of pre-established Plasmodium falciparum infection in mosquitoes by mimicking a blood meal on treated patients with artemether, lumefantrine, atovaquone, proguanil. Thank you, Priscilla. You're welcome.
Thank you very much. I've been well introduced, so there is no need to introduce myself again. I'll go straight to my presentation. So malaria, as we know, is a global health challenge, and then Africa alone contributes to more than 90% of the disease morbidity and then mortality. Currently, ACTs is the first-line treatment for malaria. However, its efficacy is being threatened with parasite resistance, and also it has limited effects on the transmissible stage of the parasites, which is the gametocytes. In the 20th century, the occurrence of drug resistance led to a dramatic increase in the disease-related morbidity and then mortality. And this emerged from Southeast Asia. And currently we see that in Southeast Asia, they've recorded resistance to these ACTs that we use. And then some African countries have also recorded resistance. Therefore, there is the need to explore more on the different therapeutic effects or different therapeutic interventions so that we can mitigate the spread of these resistance to the resistance of the parasites. So this led to a clinical trial called ASAP. It's a multi-centered in 4 African countries, and we're looking at the safety and efficacy of triple therapy in the treatment of malaria in uncomplicated malaria in African children. And the IMP, the investigational medicinal product of interest here, was artemether lumefantrine plus atovaquone proguanil. So a sub-study within the ASAP study looked at the transmission blocking activity of this new combination, since it will indeed be an added advantage if, aside the mitigating the resistance, we are also able to block transmission from human to mosquitoes. It will also help in limiting the number of new cases and then limit the spread of resistance. So how does new infections occur? So it's either, how can we, try to limit these new infections? So we can first look at killing the gametocytes or impeding the early stages within the mosquitoes. And then most work is actually focused on this, giving the chemotherapy to kill the gametocytes in the humans. We can also look at clearing an already infected mosquito of the parasite so that the mosquitoes will have no or less parasites when biting, when taking the next blood meal. And my current presentation is based on the second point. In all the ACTs we have, AL is the only one that has some transmission blocking activity by clearing gametocytes in the humans. However, it's not 100% or it's not complete. So this brings the atovaquone proguanil in picture. So yesterday I remember that Dr. Akoli mentioned how atovaquone was able to clear mosquitoes of the infection when they are given before or after the infection. It also displays multi-stage activities. So therefore it can have an effect on the development of resistance. So at the blast stage of the parasites, it provides curative treatments or prophylactic effects. At the liver stage, it provides prophylactic effects. And then at the mosquito stage, it provides transmission blocking activity. Currently, primaquine is the gold standard for malaria transmission blocking. However, there is a challenge. It's toxic to GCSPD deficient individuals. So if AP is able to do it, then we are lucky and we can bypass the use of primaquine. So therefore, this study aims to assess the efficacy of artemether-lumefantrine plus atovaquone progranil tritherapy compared to artemether-lumefantrine plus placebo bitherapy in the blocking of Plasmodium falciparum infection in mosquitoes. So specifically, we looked at how the blood of treated or exposed patients will have on blocking transmission or will have on clearing already infected mosquitoes of the parasite by inhibiting or reducing the oocyst infection rate and intensity, sporozoid infection rate and intensity, as well as inhibiting the sporogonic development. We also looked at the relationship between the atovaquone concentrations and then the transmission blocking activity. So as I said earlier, as I mentioned earlier, it's part of a clinical trial. So our samples were taken blinded. So we considered the first 24 patients included in this clinical trial, and this was done only in the Ghana site. So we considered the first 24 patients, and out of them, 19, we did the experiment for 19 patients. Samples or plasma samples were collected at these 8 time points, 0 before the first drug administration is given, and then 7 other time points post drug administration. So we have our plasma samples, and then we go to the community to look for asymptomatic gametocide carriers, and then their blood is first given to the mosquitoes during the experimental infection to cause the infection. And then 4 days after the experimental infection, we add, so during the experimental infection, we replace the donor's plasma or serum with a naive serum. This is to enhance infection. And then 4 days after this infection, we bring the plasma from the clinical trial patients. We look for all blood donors, and then we mix the plasma with their red blood cells to form a complete blood, and then we feed it to the already infected, supposedly infected mosquitoes, or the mosquitoes that fed during the first experimental infection. So samples, we collected data at different time points. So we did the infection rate, which was taken at R0, the day of the experimental infection, feeding rates, which was recorded at the 4 days post-infection, when the clinical trial plasma was given to the patient. And then 7 days post-infection, where we look at the oocyst number and then oocyst size. And then 14 days post-infection, we looked at the number of normal oocysts and then ruptured oocysts, as well as quantification of the sporozoids. And then at the end of the experiment, we did the unblinding, and then realized that 7 of our participants were in the AL placebo arm, and then 10 were in the AL-AP arm. We also collected extra plasma samples for pharmacokinetic analysis. So this first graph shows the concentration of atovaquone and then lumefantrine in the participants. So here in the placebo arm, obviously we see the absence of the AL-AP. No, we see the absence of AP, and then lumefantrine concentration rise and then peaked at 72. This was similar for the experimental arm, and then the same for atovaquone in that arm. So our 72 recorded the highest atovaquone concentration. Then this was to be expected because at that time point, all 6 doses of the drug had been given to the participants. So looking at the effect of the drugs on oocyst and then sporozoid transmission blocking activity. So this is for the oocyst, and that is data for the sporozoids, or results for the sporozoids. And then on the left here, or blue, when you see blue is a control arm, which is the AL only, and the red is the AL plus AP. So we see that comparing the transmission, so the different time points were compared to R0. We used R0 as our control. So comparing the subsequent time points to the R0 control group, we see that in the placebo arm, we didn't see any significant inhibition or increase in the oocyst infection prevalence. So transmission blocking activity actually look at the population of mosquitoes that we use, how many were infected and how many were not. That's the blocking activity, the prevalence of infection among the exposed mosquitoes. But looking at the ALAP arm, we see that there are significant reduction or inhibition in the blocking activity when in the mosquitoes that were exposed to the ALAP, and then they are highly significant at the first 4 time points post first drug administration in the oocyst as well as the sporozoite. However, we experienced a resurgence at the day 28 of the a resurgence in the inhibition activity at day 28. This was not to be expected. Looking at the half-life of Atovaquone, it really has a shorter half-life. So this was not expected, and then we are currently trying to find out more why this happened. So this is the transmission reducing activity. So this data or this resource is actually, we looked at among the infected mosquitoes, how many or what's the quantity of oocysts and sporozoites that were in their midguts. So here, in the ALAP arm, just the AL arm, we saw some inhibition at 48 and then day 5. And this could be an effect of the AL on its own. And then in the sporozoites results, we saw actually a negative inhibition. That means an increase in the sporozoid intensity at R48 as well as day 28. However, looking at the experimental arm, we saw positive inhibition. That means there was an inhibition in the oocyst and then the sporozoid prevalence. And then consistent with the TBA, the first 4 time points, here the 4 is missing, it wasn't significant, but in the oocyst, the first 4 time points post-drug administration were the most significant. And then again, we saw that resurgence in inhibition at day 28. So we looked at the effect of these drugs again on the extrinsic incubation period. That is how long, or the incubation period, how long the parasite takes to develop within the mosquitoes. So here we use the 3 proxies for estimating this. 1 is the oocyst size. 2 is the ruptured oocysts, the number of ruptured oocysts. So we look at the prevalence as well as the fraction of ruptured oocysts. So with oocyst size, we expect that when we have smaller oocyst size, then it will take longer for it to develop into the, for it to develop to be bigger and then best to release the sporozoites. So here, we saw that our 72 had a significant inhibition on oocyst size in the control arm. And the experimental arm, we saw positive inhibitions in all time points post-drug administration. And again, the first 4 time points. With reduction on the prevalence of ruptured oocysts, we saw significant negative inhibition. Again, there were increased number of ruptured oocysts in the placebo arm, and then in the ALAP arm, there were positive inhibitions, except for day 14. This was similar for that of the fraction of ruptured oocysts, where here we see negative inhibition, a much increase in the ruptured oocysts, and here there was positive inhibition, sometimes up to 100% inhibition, and then day 14, they didn't have this inhibition. So that means that ALAP treatment actually prolongs the development of the parasites within the mosquitoes. So we also looked at the relationship between the Atovaquone concentration and then the treatment, as well as the parasite exposure. So here, parasite exposure was used as a proxy for the mean number of oocysts in the control group. So we saw that there is always a positive relationship between whether transmission blocking or transmission reducing activity and then Atovaquone concentration. Looking at the parasite exposure, we saw a negative relationship between that and the transmission blocking activity. And then this means that Atovaquone works better in mosquitoes that have low infection rates, low number of oocysts, and then when we have higher number of oocysts, we don't get more than 50% of inhibition activity. And parasite exposure has no relation with transmission reducing activity. With the EIP, we saw that again, positive relationship between the 3 EIPs and then atovacon concentration, and then a negative relationship with the 3 EIPs and then parasite exposure. We finally wanted to look at if the different treatments will have effects on the survival and then the feeding rates, because if it has effect on it, it will also impact or influence, it will be of public health importance. But then, I don't know whether it's luckily or unluckily, we didn't see any relationship between the feeding rates in the 2 different treatment arms and at the different time points. So in conclusion, we say that Plasmodium falciparum infected mosquitoes, when given a blood meal on AL plus AP, they can be able to block malaria transmission compared to AL alone. And the inhibition lasts up to 5 days post-treatment, causing a reduction in the infection prevalence, infection intensity, as well as slowing down the sporogonic development. ALAP is more effective in mosquitoes with low infection, as well as benefits of the triple ACTs containing AP. As when mosquitoes are already infected and they feed on individuals who have taken this drug, they can potentially clear them or cure them of this infection. So I'd like to acknowledge our collaborators, partners, and the everyone involved in this study, especially to our group leader, Dr. Umumaiga Skufari, and then to the Burkina team. This is where I did most of the experimental infection, and then Mivijek IRG in France, where I did most of my molecular assays. I want to thank everyone, and then the entomology team at KCC at large. Thank you very much.
So thank you, Priscilla, for such an insightful study. Now we'll allow for a maximum of 3 questions for Priscilla.
Yeah, Priscilla, that was an interesting presentation. I have so many questions, but I'll just ask one. So you know that the triggers for gametogenesis, one of them is drug pressure. With this drug, if a patient is taking this drug, it is expected that once you are on an anti-malarial drug, it's likely to increase gametogenesis, commitment to gametocytes. And this was an in vitro study, right? In vivo study. Okay. So your mosquitoes were already infected, and you fed them the blood that had been treated. Okay. Don't you think that the design of the study could have influenced the outcome that you got, because the drugs themselves are likely to influence gametocytogenesis?
Sorry. Okay. Thank you for the question. So we actually, okay. So we used the plasma from the individuals who had taken the drug. But the gametocytes was gotten from healthy individuals. We did this in Burkina Faso. So we went to do community screening, and then we got gametocyte carriers, healthy individuals who we don't know whether they are taking drugs or not.
Okay, so you you didn't even know the parasite load?
We did, yes, we did do the quantification. So we included people with 72 microliters per 72 gametocytes per microliters, yeah. And then, as I said, it's a clinical trial and it's a bigger study. So other objectives of the study are looking at what happens in there. This was actually something that we were expecting to happen, that when they take the drugs, it will facilitate gametogenesis. But then these results I didn't show here. We didn't see that happening in the ALAP arm. And we haven't actually analyzed that. So we were,
Okay, I think this wasn't a direct blood feeding from the persons.
No.
Yeah, because if that had happened, then we would have expected gametogenesis to have gone up in those patients who had taken the drug.
Yes, but we didn't see that because another part of the study did that, and then the samples were brought to our lab and we did. So we realized that it hasn't been unblinded yet, but we realized that during the treatments we took samples at day 0, day 2, day 3, and day 7 for the patients who are actually taking this. We took their full blood and then do the direct membrane feeding assay directly. So we realized that from day 3 and day 7, we were getting less infection. Less, very minimal to 0.
So you think the drug has gametocidal?
Yes, I think yes.
But you don't know
and then the AL
of
also has a gametocidal effect, so it's to be expected to have low gametocytes, post-treatment.
Okay. Okay, thank you.
Okay. We can have further discussions later.
All right, thank you very much. With this study, metal lumefantrine is still an effective frontline drug against malaria. Now that you want us to use it to now target the parasite in mosquitoes, what do you think we should do? Should we use it as a vaccine, or how do you intend to achieve? People who are healthy should be giving them mosquito feed on them and reduce.
So
I mean, at the end, what do you think should be the case?
Okay. So, I mean, it would be lovely to have that. But currently, what we are suggesting is that before the ACT resistance hits us for us to record a lot of mortality, we should consider triple therapies. And this drug is given to the individual. It's not given to the mosquito. So it's used as treatment for people infected with malaria. And then mosquitoes in our environment may have picked the parasites during their blood meal, during their lifetime. So when they feed on this person who have taken this drug combination, AL plus AP, then the drug will start acting on the parasite that is developing inside the mosquito's midgut. So we are not saying that we should give it to, the study that I referenced, the pattern et al. Fed the Atovacon directly to the mosquitoes, and they completely blocked. But we are giving to the individuals and we are using the plasma later, we saw some blocking activity, but it wasn't 100% in all the cases. So, okay. We can discuss further
Please, if
later
your
on.
poster presentation is downstairs, you can go and get it down. They want to dismantle the stuff.
Thank you so much, Priscilla. Please put your hands together for her. Good people, we have to ensure that every presenter is able to do their presentation before we leave here. We still have a cocktail to attend to. The next presentation is going to be a cross-sectional study on household mosquito practices in 3 dengue-affected communities in... Okay. Oh, all right. It's Stacy. Okay, so molecular detection. Stacy Amwa. Molecular detection of tick-borne pathogens in Kumasi and increasing risk to abattoir workers. Thank you.
Good afternoon. I'm Stacey Amman. I'll be presenting on the topic molecular detection of tick-borne pathogens in Kumasi and increasing risks to abattoir workers. Worldwide, ticks have been reported to spread pathogens that infect both humans and animals. In Ghana, to meet the nutritional needs of the country, a lot of livestock are imported into the country and slaughtered in large numbers within the abattoir. The abattoir workers run the risk of being infected, especially when they come into close contact with these livestock that could be serving as amplifying hosts for zoonotic tick-borne pathogens. So there is the need to create control measures to prevent the spread of infections in the abattoir. And this can be achieved by identifying tick species and their occurring tick-borne pathogens. Few studies in Ghana indicate the occurrence of tick-borne pathogens in Ghana. And I would agree with Dr. Ado when he said that there is no tick or tick-borne pathogen surveillance in our borders. So there is no tick or tick-borne pathogen surveillance system in our borders. So these livestock are just imported into the country with whatever tick-borne pathogen they carry. And therefore, the abattoir workers during the slaughtering process end up being at risk of zoonotic pathogens due to their frequent contact with these livestock. So the main aim of our study was to determine tick-borne pathogens in ticks, livestock, and humans in selected abattoirs and a slaughter slab in Kumasi. Some of our specific objectives were to look at the diversity of tick species infecting the livestock, the slaughtered abattoirs, infecting the livestock in the slaughtered abattoir, and also to determine the tick-borne pathogens in the sample tick species, livestock, and abattoir workers, as well as assessing the knowledge, attitude, and perception of abattoir workers towards ticks and tick-borne pathogens. So this was a cross-sectional study conducted in Kumasi, and our study sites were the Kumasi Abattoir at Kase, the Swami Abattoir and the Akwetia Line Slaughter Slab at Amakum. So before the start of the study, ethical approval was taken from the KNUST Ethics Board. So in the abattoir, ticks were collected from the slaughtered livestock and kept in 50 ml Falcon tubes, whilst dry blood spots were taken from both the abattoir workers and the slaughtered livestock. So the samples were transported to the lab, and by morphological identification, the ticks were pooled based on their sex, species, and sites, whilst DNA was, and later total nucleic acid were extracted from them, whilst DNA was also extracted from the dry blood spots collected. So they were screened for tick-borne pathogens, and the resulted PCR were run on a gel, after which the positive samples were sent to Macrogene BV for Sanger sequencing. A total of 371 ticks were collected from cattle, out of which 78 were females and 293 were males. So per the morphological identification we did, Amblyoma variegatum was the predominant species, followed by Hyaloma rufipes, with the least being the Rhipicephalus sanguinis. So this table shows the distribution of tick-borne pathogens in the sampled tick species. In general, Rickettsia africae was the most predominant pathogen across all three sampling sites. And most of the Rickettsia africae were found in Amblyoma variegatum from the Kumasi Abattoir, followed by the Akwetia Line, and the least from the Swami Abattoir. Amblyoma variegatum is the principal vector for Rickettsia africae. And Rickettsia africae is the pathogen that causes the African tick bite fever found in the sub-Saharan Africa. So finding it here in Ghana, knowing very well that Amblyoma variegatum was the predominant pathogen, indicates an increased risk of infections to abattoir workers. We also found the occurrence of Rickettsia asclemani in Hyaloma rufipes. And Rickettsia asclemani causes similar symptoms like that of the Rickettsia africae. CCHF has already been found to be infected with CCHF has already been found by Ekufu Ita, where he found pathogen exposure in both the slaughtered livestock and humans. So refinding it again means that the pathogen is still present in the Kumasi abattoir, and therefore the abattoir workers are at risk of being infected. We found an association between some tick species and their tick-borne pathogens. So these were recorded as Amblyoma variegatum and Rickettsia africae, Hyaloma rufipes and Rickettsia asclemani, Hyaloma truncatum and uncultured Ehrlichia, as well as Hyaloma rufipes and Candidatus medicloria mitochondria. So this is in line with literature which says that Amblyomma variegatum is the principal vector for Rickettsia africae. Candidatus medicularia is a symbiote found in the ovaries of the tick, so they are just there and do not cause any harm. This table shows the distribution of tick-borne pathogens in the livestock and humans. Amblyomma variegatum was the predominant pathogen infecting all the livestock. Amblyomma variegatum is a zoonotic pathogen known to infect humans, domestic animals, and wildlife. Just as Dr. Ado said, it was first found in China, then France, and a previous study conducted by Ado et al., where he found pathogen in the Upper East region, where he found the livestock being infected with Anaplasma capra. So this could mean that the imported livestock really carry these tick-borne pathogens with them. Our study reports the first molecular detection of Rickettsia asclemani in goats, in a goat from the Kumasi abattoir. So this could mean that goats could be serving as amplifying hosts for this tick-borne pathogen. Theileria ovis was also found infecting sheep from the Kumasi abattoir and the Aquatia line slaughter slab. So Theileria ovis is a pathogen known to infect smaller ruminants. So for control efforts, so there is a need to know how widely distributed this pathogen is, especially its effect on smaller ruminants. Interestingly, our study recorded the first molecular detection of Coxiella beniti, Rickettsia africae, and Rickettsia asclemani in the abattoir workers from the Kumasi abattoir. So these are zoonotic pathogens. So it could mean that they either got it directly from a tick bite or by handling these pathogens. And a pathogen like the Coxiella beniti is known to infect people who come into contact with with livestock and holding part of the intestine or the placenta of these livestock. And per the questionnaires administered, most of the abattoir workers do not wear any gloves when handling these pathogens. So it clearly shows that they could be infected with these tick-borne pathogens. So the occurrence of these three tick-borne pathogens means that there is a need to create more surveillance activities, and preventive controls should be put in place to prevent the spread of infections in the abattoir. We found the occurrence of Anaplasma capra. So Anaplasma capra was found in female sheep from the Aquatia line slaughter slab. We also found an association between Theileria ovis and female sheep from the Kumasi abattoir. So from table 3, you would realize that sheep were the most commonly infected with Theileria ovis and Anaplasma capra. So this shows that for control efforts, if we target sheep, it will help in the spread of, it will help reduce the risk of infections in the abattoir. So some strains of Anaplasma were found closely related to a strain from Ghana, Greece, and Denmark. Same for Theileria ovis, where we found some strains similar to an isolate in Iraq, Egypt, and Ghana. So same thing for Rickettsia asclemani, where we found similar strains in Ghana and Turkey. So this possibly tells us that the imported livestock indeed carry these tick-borne pathogens on them. So from the questionnaires administered, most of the abattoir workers were from the Kumasi abattoir. And across board, majority of them did not have education and have been working there for over 10 years. So most of them had experienced tick bites, but do not put any preventive measures in place to avoid tick bites. They do not use any protective clothes or gloves when handling these animals, which poses an increased risk of infection to them. So these findings showed that education had a significant influence on the risk of infections. So from our study, we published, so these were publications from our study. And the molecular detection of tick-borne pathogens in Kumasi with a first report of zoonotic pathogens in abattoir workers. So I'll conclude by saying, yes, tick species are capable of transmitting pathogens that infect both humans and animals. And our study reported the first molecular identification of some zoonotic pathogens in abattoir workers in Kumasi. So these findings suggest an increased risk of infection to abattoir workers, and therefore there is a need to put effective control measures to prevent the spread of infections in the abattoir. So I'll end by saying policy should be put in place to enforce the use of PPEs in the abattoir, and also frequent educational campaigns too should be encouraged to avoid the spread of infections in the abattoir. These are my references, and I would like to acknowledge these people. Thank you.
Thank you, Stacy, for your interesting presentation. We are taking 3 questions for Stacy.
Thank you very much for your presentation. So, ask, you mentioned that Anaplasma capra and then another tick was found amongst female sheep. I want to know if there's a specific reason why they were with female sheep and not another, the males or something.
Yes, so I actually don't know. No, we don't really know.
Any other questions? Any other questions?
Please, let's give her a round of applause. So we invite our next presenter, Stanley O. Ochre, to present on a cross-sectional study on household mosquito practices in 3 dengue-affected communities in Achem Mansa district in the eastern region of Ghana.
Okay, so my name is Stanley Osafo Ochre, and I'll be presenting on a cross-sectional study on household mosquito practices in 3 dengue-affected communities in Achem Mansa district in the eastern region of Ghana. This is the outline of my presentation. So dengue fever is an emerging public threat in Ghana currently. And unlike malaria, which is transmitted by the Anopheles mosquitoes, that bites predominantly in the evening and during the night, dengue fever is transmitted by Aedes mosquitoes, whose biting activity is predominant during the day. Currently, intervention strategies are focused largely on malaria vectors, with limited attention given to Aedes mosquitoes as far as their biting activity is concerned. This requires the development of effective and sustainable intervention strategies, which may require the integration of local knowledge and practices in affected communities. Interestingly, there's limited understanding of household mosquito practices in these dengue-affected communities. And like I said earlier, most of the available intervention strategies are largely focused on malaria vectors, neglecting the unique behavioral characteristics of Aedes mosquitoes as far as their biting activity is concerned. Although socioeconomic factors may influence the implementation of intervention strategies, the extent to which this influence would affect the implementation of these strategies is poorly understood. So this informed myself and the team in my lab to assess the household mosquito practices practiced in 3 dengue-affected communities in the Achem Mansa district of Ghana, where dengue was previously reported last year by the Ghana Health Service. So our specific objectives were to assess the community awareness of mosquito breeding habitats. We also wanted to evaluate the patterns of exposure to mosquito bites in these communities. We also wanted to ascertain the prevention practices that is being practiced in these communities against mosquito bites currently, and to assess the influence of demographic characteristics on these reported prevention practices. So the study was a cross-sectional study, and it was conducted in 3 rural communities, which are predominantly into farming: Muchia, Edujan, and Otabo in the Achamansa district in the eastern region of Ghana. The sampling procedure involved the use of a systematic random sampling technique, where we use the standard prevalence formula for calculating sample size to select a total of 387 households. And in these households, the adults were interviewed using semi-structured questionnaires. The data that was obtained was summarized and analyzed using our statistical software. So there was a significant association in the demographic characteristics across the 3 communities. For gender, we found out that majority of our respondents were actually males in Edujan and in Otabo. However, in Muchia, majority of our participants were predominantly females. As far as the age grouping is concerned, we found out that in 2 of the communities, which is Muchia and Otabo, majority of our participants were aged between 31 to 40 years. However, when you go to Edujan, you realize that the age is slightly older, ranging from 41 to 50 years. In terms of educational status, we realized that majority of our respondents had received only primary education, particularly in Muchia and Otabo. However, in Edujan, majority of our participants had received no formal education at all. In terms of occupation, we realized that majority of our participants were farmers, and it was expected because all these 3 communities are predominantly into farming. However, for Otabo, we realized that majority of our respondents were self-employed in various professions other than farming. For religious affiliations, though there was some form of diverse variability in Muchia, majority of our participants were predominantly Christians. In terms of the awareness of mosquito breeding habitats and their control, 95% of our respondents indicated or were able to identify mosquito breeding habitats. However, when you look at the second graph, which is figure 8, it shows that majority of our respondents mentioned mosquito breeding habitats that were not typical of Aedes mosquitoes. For Aedes mosquitoes, only 2% of our respondents revealed breeding habitats that are used to Aedes mosquitoes, which is water in open, this one, cans and containers. In terms of their knowledge about mosquito control methods, approximately 303 of our participants out of 387 indicated the use of bed nets. Others also indicated the use of education, sanitation, the use of the zapper, as well as the call in the control of mosquitoes. In terms of the household mosquito biting experience and prevention practices, 99% of our participants indicated that they were more bitten at home compared to other places in these affected communities. Out of this percentage, 58% indicated that they were more bitten outdoors, with 34% indicating that they were more bitten both outdoors and indoors. In terms of the peak biting times in these affected communities, majority of the participants indicated that they were more bitten in the evening, whilst 19% indicated that they were more bitten in the morning, in the evening, and during the night. As far as the prevention practices that is being used against mosquito bites in these affected communities is concerned, majority of the participants, approximately 84%, cited the use of bed nets, with a few emphasizing the use of mosquito sprays and mosquito coils. There was also a significant influence of some of our demographic characteristics on these reported prevention practices that is being applied in these communities against mosquito bites. For gender, no association was found between that and the reported prevention practices in these areas. However, for education, a significant association was found. What we realized was that majority of the participants indicated the use of bed nets. However, as the education level increases from non-formal right to tertiary, we realized that majority of the participants were more likely to adopt diverse or multiple prevention practices in addition to the use of bed nets. Likewise, for occupation, a significant association was found between this socioeconomic characteristic and also the reported prevention practices in these areas. Again, majority of them were using bed nets. However, we realized that individuals that were employed in professions with high income level were more likely to adopt the use of other practices aside the use of bed nets. There was heterogeneity in the demographics across the three communities, which highlights the need to apply or implement community-specific intervention strategies in order to increase the adoption rate in these affected communities. Our results also revealed a critical mismatch in the community awareness of mosquito breeding habitats and dengue-specific control needs that we need currently in our country. This was because majority of the participants cited mosquito breeding habitats that were not typical of Aedes mosquitoes. Now, given the fact that these areas are predominantly into farming, and these farmers use water containers that are left open in their farms, and also upon field evaluation and field survey, we realized that during the cocoa season, they actually leave the pots open, which are usually filled with water because this district is actually found in an area with bimodal, rainfall pattern. So there is a heightened risk of unnoticed aiding breeding habitats in these areas, reiterating the need for mass education on the behavior of these Aedes species in order to increase the adoption rate of any intervention strategy that we are going to develop. There was also a critical mismatch in the community awareness of mosquito biting behaviors and the need for dengue-specific control strategies. Majority of the participants actually hinted that they were more bitten in the evening, and they also indicated outdoor exposure. However, we know that this is very typical of the Anopheles mosquito. Aedes bite predominantly during the day, and given the predominant farming activity in these areas, which likely provide breeding habitats for Aedes mosquitoes, there is the need to educate these people on the bioecology of Aedes mosquitoes in order to make sure that there's an increased adoption rate of the intervention strategies that we are going to deploy in these areas. We also find out that in terms of the prevention practices, majority of the participants cited the use of bed nets. Whilst this is very effective against malaria vectors, it is not very effective against Aedes given its biting activity. This draws our attention to the fact that we need to come up with innovative strategies that target the biting activity of Aedes in order to increase its sustainability when applied in these dengue-affected areas. The significant effects of some of our socioeconomic characteristics on mosquito bite prevention practices in these areas highlights the need for the implementation of equitable innovative strategies that can be easily adopted by indigenes in these affected areas irrespective of their education level or income level. This study showed that though community members in affected areas had encouraging knowledge of mosquito breeding sites in these areas, they were more skewed towards other genera of mosquitoes other than Aedes mosquitoes. There was also an over-reliance on the use of bed nets, which is not effective against the biting behavior of Aedes mosquitoes. So we recommend the use of mass education as a tool in order to increase the adoption rate and the sustainability of any intervention measure that is developed to target, or reduce the spread of dengue fever. And we also would like to postulate that the intervention strategies that is actually developed is tailored towards community needs in order to increase this adoption rate. I would like to acknowledge the University of Cape Coast and the Office of the Dean of Students, my supervisor, Dr. Kudom, and also the community members of Edujan, Wichia, and Otabo, and my lab team members. These are some selected references. Thank you for your attention.
Excellent, excellent. I agree with you 100%. I don't think we can eliminate any disease without the community buy-in. If the community is involved, maybe we'll go a long way. We will have time for some questions. Ask the most pressing question that you have.
Okay, no question.
Thank you very much for the presentation. My question is on the bed net usage. You give a percentage that they indicated a high percentage.
Yes, please.
Just remind me again on the percentage.
It was 84%.
Yes, that's very high. Usage or
Yes, please.
ownership?
Usage.
No, I don't know, because the national malaria, I think there's a data on usage, and that is less than even the 80, or is around less than even 70, if I'm right. The point is that if it's ownership, they can own it, but usage, I don't know how you assess that.
Oh, okay. So the question was actually deployed in such a way that we asked them whether they were using BedNet, not whether they owned BedNet.
Yes, but you see, was it given to them for free? Yes, so if you give someone something for free and then you come back to ask you, do you use it?
They obviously
what
say
will the
yes.
person say?
They obviously say
yes,
yes.
because if they tell you they don't use it, next time you won't give them.
Yeah.
So they will tell you that they know that people do this questionnaire because they want to find out whether they are using it.
Yes, please.
So they will tell you what you want to hear. Because the national program has a usage less than 70%. I don't know, maybe if we have someone to correct me, there is less than, yes, the ownership is 80 something, yes, but the usage is less than 70%.
Okay.
I think they observe what the best way is you seek their consent to check whether they've mounted it in the room.
Okay.
So they say that is better.
We have a previous study in this area where we assessed the usage of these nets. And we found out that even though most of them slept in the net, others were also using them as curtains. Others were also using them as fence for their backyard garden and all those kind of stuff. So yeah.
So like I'm saying, the best way is you ask them and then you seek consent from some of them just to check if it's been mounted.
Okay.
At least if it's been mounted, you can be sure that they used it. Yeah.
Thank you very much.
All right.
Thank you for a wonderful presentation. When you were presenting, you made mention of the fact that there were people complaining of the fact that they were bitten by Aedes mosquito more in the outdoor rather than the indoor, if I'm getting you right.
No. So we asked them about the mosquito bites in general.
Mm-hmm.
We didn't relate it to any species. And most of them indicated that they experienced mosquito bites. So there was a section of the study where the participants were made to identify, where we tried to ascertain whether they would be able to identify that this is a mosquito, and let's say this is a housefly. And the majority of them were able to pinpoint a mosquito. So then based on that, we went ahead to ask them, do you experience mosquito bites? And when you experience it, where? And when do you experience it? So it wasn't tailored to Aedes species. It was mosquito species.
So it was mosquito in general.
Yeah. Yes, please.
But what do you think would have accounted for they being bitten more of outdoor than indoor?
For outdoor, we can relate it to their farming activities. You know, when they go to the farm, they come back very late. They leave very early. I actually happen to stay in some of these communities to work with them. And I realized that they wake up as early as 4:30 a.m. to go to the farm. And they return as late as around 4 p.m. to 5 p.m. So this could contribute to they being bitten more outdoors compared to indoors. But there was a significant number also indicated that they were bitten both indoors and outdoors. However, it was around 19%.
Okay.
Mine is not actually a question, but I think in your presentation you made mention of the biting times when you realized that people were, and you were saying that with those who were bitten at night, and I think at night and in the evenings, that's more of a behavior of Anopheles. I think previous studies or recent studies have also shown that the Aedes also do bite at night. So now they are changing their biting patterns and even their breeding pattern. We know they breed in containers, but now most ADs are breeding in sympatry with Anopheles, even in puddles and gutters. So we should do more studies on this to be able to also at least integrate the control mechanisms for both Anopheles and ADs together.
Thank you very much for your input.
Excellent. Thank you very much. We have two more very interesting talks to go. The next topic for presentation is Awareness in Action. Malaria screening trends and insight from 7 years of community-based malaria awareness campaigns. This will be presented by Kwabena Ekene Mwafuna. He will present from where he sits, and then someone will push the slides for him. Thank you.
Good afternoon. I'm Ekene Kwabena Nwafuna from Ghana Atomic Energy Commission. And I'll be sharing some insights from 7 years of malaria awareness campaign. But before I begin, I would like to mention that I have a bit of a speech impairment, so I might need to speak at a slower pace. So I crave your indulgence and kindly bear with me. So I'll not bore you with so much background. We have heard a lot of background about mosquito and malaria. We know it's a significant health concern in Ghana. So I'll go straight to the point. So, community health campaigns and tracking of asymptomatic malaria infections has emerged as a response to the significant health concern of malaria. So tracking of these asymptomatic infections help with targeting control measures and intercepting transmission cycles within communities. So GAEC in 2017 started the GAEC Binary Malaria Awareness Campaign as a way to give back to communities that have supported our mosquito research over the years. So we do it every year. It's an annual event that's used to commemorate the World Malaria Day, at times the World Mosquito Day celebrations. So this is actually not an investigation or a study. I'm just reporting on insights from our malaria awareness campaigns over the years. It's not as if it's a conducted study. So the problem is why we are all gathered here today. The health concern of malaria and community-based screenings and campaigns help in intercepting malaria transmission. So these campaigns help us know which areas need increased efforts. So we started this malaria awareness campaign to be able to track asymptomatic infections and intercept transmission cycles within communities. So what we do in these campaigns is that we provide education to community members, provide free malaria screening. We hold a mini deba where we bring together stakeholders in the malaria control efforts, the chiefs and Ghana Health Service, the district director in Ghana Health Service, Ghana Education Service, and then we provide treatment to those who test positive. So what we do is we use the RDT test kits, rapid and easy test kits, to test for malaria among healthy individuals, mostly children in schools. And we have done this across both rural and peri-urban and urban communities in southern Ghana. Usually school-going children. And over the 7 years, we have been to Dodi Island. That's an island community on the water lake. We have been to Ochiraku, we have been to Osrungba. Osrungba is a peri-urban community near Dodowa in the Greater Accra region. We have been to Atatem. Atatem is a small cocoa-growing community in the Adansi-Azokwa district in the Ashanti region of Ghana. We have been to Kwabinya actually twice, and Atatem twice. So these are prevalences, raw prevalences of malaria. It's an asymptomatic infection. These are people who are just healthy people walking around the streets, healthy children running around the schools. They are not sick. They are happily playing and dancing in the schools. But these are the infections we get, asymptomatic infections. You can see that at that time he's recording very, very high, 54% in 2021. So we reported this high prevalence to the NMEP. And then I think the NMEP responded by distributing bed nets, PBO nets precisely to that community. And then we were there again in 2023. And the prevalence had dropped to 48.6% after that. So the insight we can get from this is that rural communities tend to have higher prevalence of malaria, asymptomatic infections, than urban communities. And this is not surprising because urban communities have better health scheme behavior. And then the solid buildings in urban communities prevent mosquito entry, but the rural communities have open eaves and limited access to health care. Also, in other time, we observed that the mosquito behavior has changed, like you heard from Linus yesterday, to outdoor biting, actually. So we saw a decline of malaria, asymptomatic malaria prevalence in at that time from 54.4% to 48%. Although we found an increase in Kwabinya and urban community, where we had an increase from 0.8% to 3.1%. And this could be attributed to just the number of samples we tested, because these are not, it's not a study. We just carry out a community campaign. So anybody that comes to us to test, we have small numbers in Kwabinya, but high numbers in Atatem. So in conclusion, this is symptomatic, moderate symptomatic infections help to monitor malaria across multiple communities and break transmission in communities, in transmission cycles in communities. We actually provide treatment to those who test positive, provide treatment to them. So these are the team members. The idea was birthed by Professor, and we all jumped on the vision in 2017. These are some pictures from our activities over the years. We like to acknowledge GAEC Binary, National Elimination Program, National Malaria Elimination Program, Nuclear Research, Nuclear Regulatory Authority, Research Science Association of GAEC, and Northstone Company. Northstone Company gave us some mosquito repellents which we distributed in the Atatem community in 2023. Also, Aglo-Good Ashanti Malaria Control Program Limited has been helping us in this also regard as well. We acknowledge everyone who has supported the Guyuk Malaria Awareness Campaign. And just before I end, this year we'll be having the campaign in Boshe, a fast-growing peri-urban community in Accra here. And so, as a way to reach out, we're asking for people interested to partner us and maybe support us to carry out this campaign. Please, you are encouraged to support us if you're interested. And before I close, I'd like us to carry out a simple survey in this room. We're talking about bed nets and usage and ownership. I want to ask, how many of us slept in the bed net last night? How many of us? My hands were not up, so I didn't sleep in the bed net.
Very, very good question. If you slept in a bed net last night, put up your hand.
I know most of us are in hotels for the workshop, for the conference.
Yes.
So we don't have that facility there. But those of us who sleep in a house, who are coming from home, how many of you slept in the bed net last night?
You didn't sleep in it? Okay, all right.
So, zero malaria starts with us, even a scientist. We are educated and we know that if you are sick, you can go to UGMC and we can go to an expensive pharmacy and buy drugs. But we are not sleeping in bed nets. We are also contributing to the malaria problem, even though we are researchers and scientists and lecturers. Yes. So please, get a bed net with a PhD. Get a bed net and sleep in the bed net with your PhD.
Yes, yes, he deserves applause. Put your hands together for him. Governor, thank you so much for your talk. It's very, very interesting, and I admire your resilience, overcoming all difficulties, doing the science, and then staying through to the end to give your presentation. You truly deserve an applause. Please, yeah, thank you very much. So we will allow for some questions after that. Then we'll have our last talk and then the cocktail.
Yes, we need to collaborate. So this is a very interesting and very important presentation, and that is because I know Greater Accra region is one of the sites that the NMEP wants to target for elimination. The point is that what is the contribution of asymptomatic individuals to malaria transmission? And that is something that we, the entomologists, should be thinking about. So if you have people walking around, they are not sick, they are carrying the parasite, are they contributing to transmission? Yeah. Are vectors biting them, picking the parasite and giving it to others who may fall sick? And then, so it's very important to understand this, whether we need to do MDA in Greater Accra or, I mean, what will be the approach for elimination? That is the question. I think that we should be thinking of, and the chairperson mentioned it at the beginning, that we should be thinking of MDA if we want to look at elimination. Thank you very much.
Mine is not a question per se, but a comment. I have been asking the same questions that he posed. Anytime I teach, and you realize if you have to ask how many of us have ever owned a net, everybody will say, I've had a net at one point or the other, but we don't really use it. Now, when it comes to malaria control, it's very complex. We cannot use bed net alone. We talk about integrated vector management. It's not just that alone. We also have to change our behavior. In Greater Accra, we have high transmission rate, what are the drivers? Because we have, in quotes, good housing. But you realize that night activities are a lot. Church services in the night, clubs, pubs, and so on. So it's not just the nets alone. We have to look at the problem holistically, and we all play our role towards effective control. Thank you.
Will be given by a climate scientist from the Department of Meteorology and Climate Science at Kent UST, a senior lecturer in that regard. He will be speaking on climate-driven changes in seasonal malaria transmission in Ghana, timings, spatial variation, and future changes. Dr. Edmond Yamba. You're welcome.
Thank you very much. Okay, so as you mentioned, my name is Edmond. I'm a climate scientist and very much interested in climate-driven vector-borne diseases. I also do more of heat-related diseases as well. So at KNUST, I tend to work with Kingsley a lot because because of the way he deals with mosquitoes. So today I want to kind of like share some thoughts, some works on climate-driven changes in malaria transmission, and I'll be doing that using the case of Ghana. Okay. All right, so by way of introduction, of course, we know that when it comes to Africa, it's a region of malaria, and we know that story, but one of the reasons we have more malaria is because of the dominance of malaria vectors. And at least research has shown that in our part of the world, we have most of the dominant malaria vectors. We also know that climate plays a big role. And in our part of the world, our climate is very suitable. So we know that temperatures between 16 degrees to 40 degrees is very suitable for malaria transmission. And this is because temperatures below 16 degrees, the parasite usually does not survive. And when temperatures are from, say, 30 degrees and above, mosquitoes go through what we call heat stress. And from 40 degrees onwards, they begin to die. And then relative humidity, at least from 60%, very suitable for malaria, mosquitoes' survival. And then rainfall also playing a role. The issue is we are aware that anthropogenic climate change is playing a key role. And we know that temperatures are increasing, rainfall is becoming variable. How are these climate variables playing a role in malaria transmission? So if we are able to understand that, we can see how we can operationally include this climate information in malaria surveillance. So what I'm going to talk about will focus on Ghana, and it's going to look at the different climate zones. You have the Sudan, Guinea, the transition, then the forest zone and the coastal areas. The data that I'm going to use, like to give you the talk, is going to be temperature, rainfall. Then population density will come in as part of the modeling job. So the modeling work that we did, one were in two folds. One was to look at just simple climate equations or temperature-driven equations, and then another one is using a very sophisticated malaria model. So the very first ones here, I think these are familiar. You have the vectorial capacity, and by this, we're looking at the capacity or the ability of the mosquitoes to be able to transmit the disease, and want to see how temperature is influencing that. And you also have the survival probability. So if you look at the vectorial capacity equation, You can see the survival probability. You also see what we call the extrinsic incubation period, when one of the presenters was using those terms. So the survival of the mosquitoes is driven by temperature, and in these equations you see where you see T is kind of like the temperature there. So we kind of calculate the temperature-based survival of the mosquitoes using this equation, and then we can feed that back into this particular equation to determine the transmission capacity. You also have the extrinsic incubation period, which is also driven by temperature here. And the idea is also, this one has to do with the number of days that the parasite is able to survive, develop within the mosquito. And so we feed that back also into this equation. And then you have this one, which is the frequency of bites. So how many times that mosquito bites people, and you have that here. And this is so the sophisticated malaria model that we use to do the simulation. So this is just by way of giving you an idea of what the modeling work was done. Yeah, these are some parameters that we use. So just a few results here. What you see here is just to show you climate trends, so the variables. This part is showing you the anomalies in temperature. And when I talk about anomaly, you have like the average temperature, and then for the long term, how is each year deviating from, let's say, the average temperature. So when you look at the deviation on a long term, you can see that within the 5 different climate zones, you can see that the anomalies, the temperatures are kind of like increasing. And for most of the areas, we can find temperatures going as warming as up to about 1.5 degrees. So averagely, we can say that across Ghana, from 1991 to 2023, the temperatures has warmed as far as 1.5 degrees. If you look at an area like the transition zone, we can see almost about 2 degrees or so. So the right side here is the relative humidity. And we can also see a downward trend in the relative humidity, which means that averagely across the country, in most of these climate zones, relative humidity is declining, temperatures are going up. Initially, I mentioned that all these variables have an impact on the mosquito. So if temperature is rising, what's happening to the mosquitoes? If relative humidity is also going down, what's happening to mosquitoes? Because these things influence their lives a lot. So this is also some results just to show you on the lifespan. So we calculated the lifespan of mosquitoes across each of the areas. And this is a spatial map that is showing us every month how many days mosquitoes are able to live. Okay. So if you look at the dry season from January to December, you see the northern parts in this particular months, March, April, May, and usually these are the dry season months. And you can see that mosquitoes usually don't live long, so you can have like up to about 8 days they're able to survive. But during the rainy season, at least most parts of the country that they can live longest are the southern parts. So if you look at the Ashanti region, the forest areas, and part of the coastal zones in these months, you find them living up to about 14 to 15 days. Okay, but during the dry season, they don't. So this is an average spatial map within that period. But let's look at the long-term trends. So this part is telling us also from the 1991 trends till now, what's happening. So we can also see that there's a downward trend. So mosquitoes are actually not living long anymore. So if you look at for all the different climate zones that we can see, so their lifespan, lifespan is reducing. So the second one is the extrinsic incubation period. And again, so we can see that the extrinsic incubation period is also getting shorter, we saw from that equation that is driven by temperature. So which means that if temperatures are going higher, it means that the time taken for the parasite to develop in the mosquito will also become shorter. And then you can see that. And on a long-term trends, we see also declining, which means that it becomes shorter for the parasite to develop in the mosquito. Then we have the vectorial capacity, where, so for this one, we try to classify them, and based on the classification, if you have anything less than 0, less than 1 rather, then it means that the ability to transmit parasites is terribly low, or very low. 1 to 5 is more like very low transmission. 5 to 10 is like moderate, and above 10 we have like high. When we did all those computations, we saw that across the country, the transmission capacity was less than 10, which means that the malaria transmission potential of mosquitoes are also being impacted. So we are not getting like transmission is now is not high anymore, but maybe low to moderate transmission. On the long-term trends, we don't see any. We see only the interannual variability. So you don't see any trends. In some of the zones, we can see like a transition zone. You can see some kind of trend. Okay, but generally you don't see any significant trend among them. But what's important here is that transmission is kind of like not high anymore, but maybe low to moderate, low to moderate. I also show you an example of a simulation that we did, and this is for malaria cases. And here, for example, is symptomatic cases across the country. And I tried to compare 2 different climate periods. So this is historical, so from 1991 to 2020. And here, trying to see what the future scenario is going to look like. So from 1931 to 2060, what will the scenario look like in terms of malaria cases? So if you look at, again, this month, you have February, March, April, virtually cases are very down. Virtually you don't have cases, or they are there, but very, very small, if you look at the legend here. And you might begin to see more starting in the months of May, in the southern part, and then spreading upwards the north. And so by the rainy season, July, August, you see peak cases in August, downward that way. But you can see that like in the future, May that you see the southern part high cases, you see that they are reduced. Even you could see some kind of like the southwestern corner of the country in April, you could see some transmission here, but they are also drastically reduced as well here. And you would, in the southern part, you see months like September, October, you will see some kind of downward cases, but this month you see that in future, you see all of the months transmission throughout all of the months here. So again, this comes back to the fact that you are going to see climate changing in the future, and because climate is going to change in the future, you are also going to have your transmission months also changing as well. So in conclusion, at least we use climate models, at least just to tell what the lifespan of mosquitoes will look like and their transmission capacity. We could see that across Ghana, temperatures have warmed over 1.5 degrees. We can also see that the mosquito lifespans are going down, decreasing. The extrinsic incubation period is getting shorter. And it's getting shorter. Bacterial capacity is also now low to moderate, because then we don't see any high transmission as well. And so if we are going to look at this particular information, and because you are dealing with vectors, I think that this information should be very interesting to you, especially when you want to target your interventions. Right, so that's it. Thank you. And this is my, if you want to reach out to us, you can reach us through this contacts. Thank you.
Thank you very much, Dr. Yamba. Please, any questions? You didn't understand the equations? Yes, please.
Okay, thank you. I think maybe would you like to go back to one of your slides, maybe probably, and where you're talking about the temperature. Yeah. Okay. Good. So I realized that you made some map, heat map across the country, and I want to ask if the temperature variability in the southern part or the southern belt, and then the forest belt, and then the Sudan, as you mentioned, how variable is it among each of these category? And then whether that also tends to have an effect on the vectorial capacity, as you mentioned.
Yeah, so thank you. So this is the, a climate map here, and this one is actually not based on temperature, okay? But here in constructing this map, we use temperature, rainfall, relative humidity to construct this, and that was able to help us know the different climate zones that we have here. But if you look at the temperature variability, usually temperatures are higher in this particular climate zone, followed by this. And if you look at the trajectory of climate temperatures, they look like this. And the temperatures are warming and stretching across whole area and going down to this this corner of the country, okay? And you also see that, so here is much more colder, not much colder, but at least this is, if you look across in terms of temperatures, this is the region that is more like quite good. The climate here along this, all the coastal areas here now mimic a little bit of what's happening here, okay? The difference here is that the humidity here is higher compared to what you have here. So you have relative humidity influencing the temperatures and rainfall here a little bit compared to what's here, okay? So these differences in the climate variables actually have influence on the lives of mosquito in these all the different zones that you see here.
Okay. Can we go to the model, please? I think I saw where you talk about the goniotroffic cycle and
which one?
The model.
This one?
The
model. Okay.
Your model?
Yeah.
Yes. Okay. Okay, I've seen it. Thank you. It's okay. That's okay.
Thank you, Dr. Yamba, for the presentation. It's really insightful. And I find it really, important for public health as we are looking for innovative ways. If this model, in a way, is kind of limiting infection prevalence and other things you've kind of highlighted. But then I want to know, did this model consider data sets, as in what has been done previously, infections and other stuff? And if yes, what were data that were considered? And possibly, I don't know whether it's a question or suggestion, but looking at the vector behavior, they adapt to suit, conditions so that they can survive. It's a trend that we've seen over the years. So now I'm also, I don't know what I'm saying, suggestion or to look at if we can have a model that can predict the adaptation to suit this new condition for the vector. I don't know if it's something that we can consider, and if maybe, I don't know your thoughts on that as well.
Yeah. Please help me again with your first part of the question. You said whether I considered something. Okay. Yeah. So let me start with the last one. As for modeling, we can always model anything as long as there's data. And that's why sometimes when you are doing the modeling, we want to rely on all the research that you people do. So if you if you do research and you have some of the parameters available for us, we can always use them to do that kind of modeling. Okay. So if you look at what I did here, I relied on just temperature and looking at how it has influence on the vector. If I have data on, let's say, you're able to identify a resting site, and then we're able to characterize the microclimate of all those resting sites, we should be able to model that as well. Okay. So all of that will depend on what data is available for us here. And also with the modeling, for example, apart from this, see, I also considered some probabilities here in the models. So if you look at this, in one of the equations, we included the human blood index. You also look at the probability. So if the mosquito bites human being, what is the probability that it will transfer the parasite to the human being? And then the other way around, from the mosquito, it's from the human being to the mosquito. So all those things were formulated, and you have some probabilities estimated and then included in the equation. Okay. So most of the parameters, we look through literature and what the researchers like you, what you have done, what you found, and then we use such information in the models to be able to make our predictions. Right.
Thank you so much. Your presentation is very insightful. But my question is, you are showing some parameters which you included in your model. It's a predictive model. And I wanted to find out with the heat map that you showed based on the temperature and the survivorship of the vectors, is it possible to include or adjust the model with other factors which could influence the survivorship of the vectors? Because I know some of the vectors, especially in high temperatures, would have certain mutations like the inversions and the heat shock proteins, which could also influence their survivorship. So maybe if the model is adjusted with some of these parameters, we can have what is really happening on the field, and it is also going to help with the control strategies.
Yeah, so when I was presenting, I mentioned that, so this particular model is available. And I was saying that this is much more sophisticated. These are just simple relations. So in this particular model, for example, it takes in all these complicated parameters. So for example, here, you are looking at the larval stage here. This part of the model is looking at the larval stage. And within the larval stage, you are looking at how the mosquito is growing within water. And within that water-bound stage, what's the water temperature like? What's the effect of the water temperature on it? What does it feed on? Do we have other organisms that are feeding on it and influencing on them, how many of them would survive at this point? And then once it grows from the larval stage into the vector, you're also looking at their survival probability. So based on like other things like here like this, they include mosquito nets, they include like spraying and other stuff, okay? And then here you also include the population density. How many people are they biting? So if I run this model for, let's say, a rural area, the output I will get will look different from if I run it for an urban area, because then you have more people in an urban area compared to a rural area. So, but because the presentations were looking so short of time, I couldn't give you all of the results here. But we have information for all of this that can help us.
I think it's building on what Somwa and he said, is the unpredictability of the mosquito itself. It has the capacity to adapt. So if you spray indoor so much, it decides not to sleep indoor anymore, not to rest indoor, it will rather choose to bite outside and sleep outside. And so it's interesting to know that increasing temperatures are reducing the lifespan of the mosquito. are also reducing the bacterial capacity. But the mosquito itself, we don't know how it is adapting to the temperature itself. So it may be possible that some mutations will cause the mosquito even to become resilient even with increasing temperatures. That's what we don't know. But for modelers, they will need that data in order to put in the model to do that adjustment. But it's something that we should all be preempting because mosquitoes are not predictable. Thank you so much. We've come to the end of this scientific section. You have been full of energy, very interesting, asking questions and engaging. It's been one of the very wonderful things that we have done as Pamca this year. I know announcement will come, president will come, but let me just say that the organizing team that is headed by Joelna has done a very wonderful job. President and Joelna, can you come here as we give the announcement? Yes. Put your hands together for them. Put your hands together for them. A lot of work have gone on behind the scenes, but they are the face that representing the very hard work that has gone on. Thank you so much. It is the announcement time. Put your hands together for them. Thank you so much.
Yes, so thank you very much. So I think that tomorrow we will have a few activities. I'll hand over to the MC to give you the announcement. But there are subcommittees that have done so well. We have various subcommittees. And Danielle is one of the persons that have been very instrumental in the work that we have done. She was in charge of the communication subcommittee. A round of applause for her too. And so they have been in charge of the designs that we've seen here. And if you see the abstract book, I'm sure you've seen it. The design with the Ghana map in there, she led that for them to do that. As Madame also led the content. So the chair of the scientific committee with her team also looked at the content of the abstract as we saw. So arranging the various abstracts and putting in the messages from the leadership and all that. And that, so the content and the design from the two ladies. Woman empowerment, isn't it? Yes. So we have various subcommittees. We'll introduce them tomorrow. But we also have the rapporteur subcommittee. They are behind there. You may not see them, but they are also doing a lot of work. A round of applause for the rapporteur subcommittee, led by Dr. Seth Ado, the TIC man, the man who presented on the TIC. So we also have Andy Asafweje. I'm sure you know him. The organizing team, you won't find them in the auditorium, isn't it? They are working behind the scenes. So we have Andy Asafweje, also the chair of the subcommittee. And in fact, we also have key individuals. For example, we have a lady there, Rebecca Poalia. If you don't pay, you won't enter. I'm sure you met her. She's more like the treasurer. And so it's been a very great team. I'm just saying this because tomorrow they'll be introduced. And during the award session, we'll highlight some of these things. But I'm so excited about what we have done as a chapter. We've sent a signal to the headquarters and everyone to show that we can do it on our own. We don't need organizers anywhere to organize anything for us. And so we can host even an international conference. And I think we should all clap for ourselves and we are proud of it. So we'll talk more about most of the activities, but for now, let's hand over to Danielle to give us some announcements.
All right, so Dr. Frimpong rightly acknowledged a lot of key persons that helped with the organization of this conference. And the past 2 days have been heavy in terms of content. We've gone through everything from vector surveillance and monitoring systems. We've seen the use of modeling and AI to augment our vector control efforts. We've looked into population genetics. We've had students do table talks. We've run about the circles of One Health. We've seen presentations on black flies. we've seen bed bugs, and we've seen ticks. So we've gone from just mosquitoes into integrated vector control. And at this time, we've come to the end of today's proceedings. Just a moment. I'd like to acknowledge our sponsors. We had presentations from the 3 platinum sponsors, Syngenta, Mitri, and EK Brand Consult. We have other sponsors which were categorized into gold, which are Noguchi for giving us this space for free. And we also had support from Health Alliance Network. Also, we had LabMat and AMCOVEC project from GAEC supporting us as well. Tomorrow, we would be repping live in our t-shirts. So if you haven't picked up your t-shirts yet, please do, and wear them tomorrow. Tomorrow we'll have the AGM, and after the AGM, we'll take a group picture, the final picture for the conference. We will be starting at 9 a.m., so please come on time. Let's register and have the AGM quickly, and then have a nice closing ceremony. The closing ceremony will follow the AGM. And before the closing, actually for the AGM, for members of Pamca, the Constitution has been shared in the WhatsApp group and I think via emails. Please go over that so that the deliberations here would be worthwhile. A team link will be provided for members who are joining us virtually, and so you can participate in the meeting via that tomorrow. Internet will be available for participants here if you need to access the Constitution online. After the AGM, we'll have the closing ceremony where other people would be acknowledged. We'll get to meet key persons and also award those who have done a very good job. Thank you all for being here today, and we'll see you tomorrow. Enjoy the cocktail hour.
On the program, we have the AGM starting at 10. That's what we wrote. But I think we need more time than an hour and 45 minutes to discuss issues. We haven't met as Pamca in a very, very long time. So we are urging all of us to actually come and start at 9 rather than 10, as it's written. So the AGM is not starting at 10. It starts at 9 tomorrow morning. So we can have enough time to deliberate on issues. Thank you very much.
Thank you all, and enjoy the cocktails. Bye.